So very good evening to all. So today we'll be discussing on Blackboard. You can see. So yesterday, see, you people may be having a doubt that if I write it on a blackboard, the PDF will be black. No, so you'll get it in white only. Don't worry. You see, so blackboard is more convenient compared to your whiteboard. You check, right? You'll see, right? And one request is, yeah, Prakash. So you can see this is a black. So I'll make it completely black. So lines also will just make it little bit bigger. Right. So this is the blackboard. You can find comparatively the good vision, right? You can see. So yesterday, because of this network issue, some of the students are unable to follow the post-break session. So what I will try to do means I'll try to repeat that once. After that, we'll continue the discussion today, right? We'll see, right? Jitendra, the Wi-Fi shifted. It is next to me, right? It is next to me. So yesterday, whatever the issues I have, I tried to resolve it. Even I spoke to that Wi-Fi people. They came in the morning and they rectified a lot. So now it is clear. I think the sound is clear. So please text me sound and everything. You can see. So I'm moving the board now. Board is also moving. Right. You can see the board is moving. So just I'm moving. Right. Thank you, Baba. Right. So I'll continue the lecture today. So yesterday I was discussing about the features. So those who already learned this, so please try to feel that it is a revision. Why? Because yesterday some of the student told me that, so after the break, right? So I'll discuss once again. So features, features, features of induction machines. And one more thing is the very, very important concept is that rotating magnetic field, which we are going to see immediately after this features. Please see induction machines. Induction machines. The first point is, as I told you that this induction machines works on mutual induction principle, just like in case of transformers. So what is the meaning of mutual induction principle means? So here, whatever the current that flows in the secondary winding, so here in case of induction, we call it as the rotor winding, is not from a separate source, but it is due to the induction. What do you mean by that? See, if you recall the transformer, so a transformer consists of a core, core, and will be having a pair of windings. So basing on the number of turns, we'll define either LV or HV. So I think you know that we don't have primary winding and secondary winding. So we name that winding as a primary winding. If you use excitation, then the other side will be the secondary winding in that case. But here, generally a transformer will be having LV and HV. See, when I give the excitation to this, let the number of turns be N1 and the number of turns be N2. So because of this excitation, the primary will draw a magnetizing current. I'm neglecting the last component. So this number of turns into the magnetizing current will produce as one MMF, and this MMF will drive the flux, and the nature of this flux will be basing on the nature of this current. As the nature of that current is alternating, the flux which is passing through that core is also alternating. So when I'm talking about alternating flux, so if I'm trying to just plot it, so with respect to time, then you can see if the flux magnitude is 0 here, then I can say in the core, the number of flux lines passing are 0. Then with the time, as the magnitude of flux is increasing, the number of flux lines passing through that core are increasing. Then you can see on the core, we'll be having windings on two legs. So flux lines are passing inside the core, and on the core we'll be having winding. But whatever the flux lines those are passing inside the core, they are not fixed. They are varying with respect to time. Now, if I consider at omega t is equal to 0, the total number of flux lines passing are 0. But with the time, the number of flux lines passing through that core are increasing, are changing. And you know that according to Faraday's law, if in a coil, if the flux lines are changing, then the flux linking with that coil will be changing, and hence an EMF is induced. So I call the EMF induced in the secondary winding as E2, and the EMF induced in the primary winding, we call it as E1. And that EMF, we call it as a back EMF, right? Then if I connect a load here, then this load will carry a current. You can see current, whatever the current that flows in the other side, the secondary, is not from a separate source, it is from the induced EMF, or that current we call it as induction. So please remember, as the current which is flowing in the secondary is due to that mutual EMF or mutual induction principle. So we say that this transformer is working on mutual induction principle. Now, if I'm talking about a induction machine here, just like a transformer, even an induction machine will also have two sets of windings. So one set we call it as the stator winding, just similar to your primary winding. The other set is called as a rotor winding. So this one is a rotor winding. So I'm just drawing only single phase, but whereas in case of three phase, we'll be having three windings. Let me complete that also, no issue. So here, just like your transformer, we feed a three phase supply here, only one supply is given. But whereas the current in the secondary, that is called as the rotor winding, is due to induced, or that currents will be induced current. So here we are not giving any separate three-phase source to the rotor winding. So whatever the current that circulates in the rotor winding is due to induction principle, and EMF will be induced. Why we'll see in the coming days. So that EMF, as it finds a closed path that circulates a current, that current we call it as induced current. So you can see even here in case of an induction motor, whatever the current that flows in the rotor windings is due to induction principle. So on that basis, we call it as a induction principle. But tomorrow, if anyone questions you, what is the law which governs motoring, means it is the Lorentz law. What is the mathematical form of that Lorentz law? F is equal to BI, right? The mathematical form of that Lorentz law is equal to F is equal to BAL. That means every motor has to satisfy these three conditions. What are those three conditions? BIL. So the current carrying conductor has to place under a magnetic field to have a mechanical torque, right? Mechanical motion, that we'll see later. But as of now, with respect to this principle, so on which principle it is working means induction principle. But if you recall a DC motor, DC motor. So in case of a DC motor, if you recall, in case of a DC motor, if I'm talking about a DC motor, so in case of a DC motor, we'll be having a field circuit, and we'll be having a armature here. And on the armature, we'll be having the armature conductors, and those armature conductors are excited separately with the help of a DC source. You can see the currents in the armature conductors are due to that supply current. So we are giving a separate source to the winding. So these motors, we call it as conduction motors. On what basis we are calling it as conduction motor means we are using a separate source to supply the currents into the armature winding. So that is the reason they are called as a conduction motor. But here, this is a induction motor, On what basis I'm calling it as an induction motor means whatever the current that circulates in the rotor winding is not due to a separate source, but that current will be due to induction principle. EMF will induce, that EMF will establishes a current, and that current will make the rotor to rotate. How, we'll see in the coming days. So the first point to be noted in features is, so it works on the mutual principle, mutual induction principle, just like a transformer. So can I give a statement? It works on right. So it works on mutual induction principle, just like a transformer. See, once you are familiar with this induction motor, we are going to see the differences between a transformers and induction motor. We'll see, right, whenever the time comes. So during the time, I'll be just comparing these two, right, please. So you can see here, once again, I'm discussing about the first feature. First feature, what is that? It works on mutual induction principle just like a transformer. On what basis I'm calling it as a mutual induction means whatever the current that circulates in the secondary is due to that induction principle. I hope this point is clear. Please confirm me all of you. Please confirm me all of you. Right. Done. Now the second point to be noted here is, one second, let me just, so morning I had one more class. So morning for BTech I was discussing synchronous machine. Right. Second point to be noted here is, see, so as I told you that in my last class, if we want to transfer power, so in which case we are going to transfer power means in transformer, we are going to transfer the electrical power from one circuit to another circuit without any change in the frequencies by varying this voltage and currents. So if you want to transfer the power, so how many fields or how many magnetic fields are required? Two magnetic fields are required. Even in case of your DC machines or synchronous machines or induction machines, as these are the electromechanical conversion devices, as we are going to convert one form of energy to another form, even here also we need two magnetic fields. Unless and until there are two magnetic fields, so there is no concept of power transfer, there is no concept of the power conversion. I will repeat that once again. Please see. If you take a transformer again, even induction machine is equally applicable. Then you may have a doubt, sir, why you are taking a transformer. So it is very similar to the transformer. That is the reason in starting days, starting hours, I'll be comparing with the transformer. Please understand. If I'm taking a transformer, so as I told you that a transformer consists of a stationary core, standing core, and we'll be having the pair of winding like this. So we connect the load across the secondary. So load is not directly connected to the primary, so it is connected to the secondary, and there is no electrical contact between these two windings. But how the power is going to be transferred, that is the main thing. So here, let the number of turns here be N1 and the number of turns here be N2, right? So whenever I give an excitation here to say one of the winding, then I name that winding as a primary winding, just like in your first feature. So this N1 into I mu will produce as a MMF. Thus MMF will produce as a field, and that field links with both the windings, and hence an EMF is induced in both the windings. EMF is induced in both the windings. And this, the current drawn from the source is approximately V minus E by the Z1. So Z1 is the impedance of your primary winding. So when I'm not connecting any load, so the magnitudes of V and E1 will be almost the same. And we can name this E1 as a back EMF. Back EMF. And that plays a key role in balancing the power. So that plays a mediator between the two windings for transferring the power. How you will see, right? See, if you remember E1, so E1 is equal to 4.44 phi m F into the number of turns per phase. Turns per phase. Then you can see there is no load connected. When there is no load connected, you can see only one field or only one flux is present in the core. That is the main flux. When you can find only one flux in the core, so there is no concept of power flow. As I told you that if you want to transfer the power, so how many fields are required in the core? There should be two fields. Now what do you mean by that? See, when I am connecting a load here, so this EMF which is induced, we circulate a current I2. So this N2 into I2 will produces one more flux, and this flux will try to oppose the main field flux. Oppose the main field flux. So because of the flux lines which are coming in the opposite direction, so the flux in the core will decrease. So during that instant, when the flux in the core decreases, so as flux in the core decreases, E1 decreases. When E1 decreases, then V minus E1 will increases. When it is increases, it is drawing some additional current. So as a result, the current drawn from the supply will increase. When current drawn from the supply increases, V into I1 will increase. So that means the power drawn from the source will increase. So that additional power where it is going means that additional power is going to that secondary, or that additional power is going to the load, right? So Kiran. So once again, whenever I connect a load, what circulate? A current. So that current will produces one more flux. That flux will oppose the main field flux. Because of that, the flux in the core will decrease. The back EMF E1 will decrease. When E1 decreases, V minus E1 will increase. When V minus E1 increases, current drawn from the source will increase. And that current, additional current, what is being drawn, that V into I1 is going to be increased. The power drawn will increase, and that power is fed to that load. In other way, if you have attended the transformer class, your teacher might have told you that. So whatever the additional current that is being drawn, I2 dash will produces one more flux, phi 2 dash. And this phi 2 dash will cancel out that phi 2, and the flux in the core will remain almost constant. Like that, your teacher might have told you that, and a transformer can be named as a constant flux device. Your teacher might have told you that. That is true. But with respect to power flow, if I want to tell, so I'm calling myself as a load across the secondary. I need to communicate to the primary, or please draw some power and give it to me. Then how I will communicate to the primary means, so whenever the load is connected, so a current circulates. That current into that number of turns will produces one MMF that will drive one more flux. We call it as a secondary flux. That secondary flux will start opposing the main field flux. Then at that instant, what happened to that flux in the core decreases. Then E1, the back EMF will decrease. B minus E1 will increase. Current drawn will increase. Power drawn will increase. And where is that power going? Means the power is going to that secondary, that is going to the load. So here, if you want to produce two fields, so how many electromagnets we are using here? Two electromagnets we are using. So this I name it as one electromagnet. So you know that electromagnet should consist of a core, winding and excitation. And I can treat this one as a second electromagnet, core, winding and current. So here, so to produce two fields, two magnetic fields, we need two electromagnets. And you know that electromagnet should consist of a core, winding and excitation. But here for the second electromagnet, we are not giving excitation from a separate source, but whatever the excitation that is given or that is there, it is due to induction principle. So on basis of how many excitations we are giving, so how many excitations we are giving here, only one excitation we are giving only to the primary. But it doesn't mean that the secondary don't need excitation or current, but we need. But how that current will flow means through induction principle. But whereas in case of a DC motor, if you look into this, so the field windings are excited separately with a DC source, and the armature windings are excited separately with a DC source. So that is the reason it is called as a double excited. But here, how many excitations you are using? Only one excitation. Just like this, even in case of an induction motor also, induction motor also. So if I'm calling this one as a primary winding, so the excitation is given to this primary winding, that is stator winding, but whatever the current that flows in the rotor winding is due to the induction principle. So here also how many magnetic fields are required? Two. One is the stator field, the other one is the rotor field. So for rotor field, so from where we get that current means the current will be due to induction. So if I want to count how many sources are required here to produce two fields, how many sources are required to produce two fields means we can say only one source. That means we are giving to the stator, but whatever the rotor, how the rotor windings are getting the current means due to induction. So overall, how many excitations we are giving to this induction motor means only one set, that is one three-phase supply. But if you take a DC motor, how many excitations we are giving? Two excitation. One is to that field winding and one is to that armature winding. That is the reason it is called as double excited, but whereas this one we call it as a single excited machine. So just like a transformer is a single excited, whereas induction machine is also a single excited machine. So is this point clear? Confirm me, Kiran. Confirm me, Kiran. Right, done. So can I say, right, right. So can I say it is a single excited machine, just like a transformer, just like a transformer, right? So these are the two features as of now basing on the construction, right? See, one question, why E1 is called as a back EMF? See, Baba, there is only one winding. We are giving excitation to that winding. So in the same winding, there is one more voltage which is acting in opposite direction. If you apply the Lenz's law, so you can see the polarities will be like in 180 degrees phase shift. As it is in opposite direction, it is called as a back EMF. Your transformer teacher might have explained. So that voltage we call it as a back EMF. And even the same concept will be there in induction, and that back EMF plays a key role. So it is a key role. If there is no back EMF, there is no concept of motoring. So anyhow, I'll discuss that. Don't worry, right? Sir, DC only one phase. No, Bob, it is not one phase. It is called as a two phase. Why? Because you can see for field, we'll give one excitation. For armature, we give one excitation. So it is a double excited, right? Sir, can transformer be called as a machine? No, it is a device. A transformer is a device. So only with rotating parts, we call it as a machine, right? Please, done. I hope this point is clear. So don't worry, right? I'll explain why it is called as a back EMF as of now. Remember that. So these are the 2 points. So what are those 2 points? See, Baba, Mr. Anonymous attendee, try to keep your name. Anyhow, no problem. I'll answer to you. Sir, why the extra flux produced by the primary winding not set up another another back EMF? Why this process not become cyclic? See, these are all like transient conditions. Transient conditions means so that secondary field will reduces E1 main field. This main field will reduces E1. So as a E1 is reduced, V minus E1 will increase. When V minus E1 increases, current around will increase. So that current will produces one more flux. These two fluxes will get cancelled and flux in the core will remain same. So whatever the reduction we have in E1 due to this phi 2, it is compensated by the phi 2 dash, and hence that phi or the flux in the core will remain constant, right? I think this point is clear. Is this point clear, all of you? Right, done. Yes, rotating part is a machine, whereas stationary part is a device, right? So these are some points to be noted as of now with respect to your construction, right? So first point is it works on mutual induction principle, just like your transformer. The second point is it is a single excited machine, just like your transformer, right? Now let us go for rotating magnetic fields. Very, very important concept. One is supposed to understand this. Rotating magnetic fields. Magnetic fields. So in cut short, I'll write it as RMFS, rotating magnetic field. So already we have seen in yesterday's class, if anyone questions you or how to produce a rotating magnetic field, means you can answer like this. Take a bar magnet, connect that bar magnet to some external prime mover, and with the help of that bar magnet, see that the poles are rotating. When the poles are rotating, the magnetic field lines will rotate. When the magnetic field lines are rotating, the flux around will also rotate. So that is one way of producing a rotating magnetic field. But very unfortunately, what is the main problem we are having with such rotating magnetic field is, as we don't have any control over the magnetism or the field produced by this magnet, so the flux or the field magnitude is uncontrolled. And if I'm using such rotating magnetic field in case of generator, the output voltage will be uncontrolled. So we don't have any control over controlling the magnitude. When output voltage is uncontrolled, so that voltage will produces a current, voltage into current is power. So we don't have any control over that output electrical power. So in case of a generator, if I'm using a permanent magnet, the output electrical power will be uncontrolled. Similarly, if I'm using a permanent magnet for rotating and producing a rotating magnetic field, then output mechanical power is also uncontrolled. So to rule out that, we can design one electromagnet. What is that electromagnet? Take a core. On the core, place a coil, and through the coil, you pass a current. Then that will produce a magnetic field. And if you connect that electromagnet to some external prime mover, and if you try to rotate that electromagnet, the field rotate and the flux will also rotate. So like this we can produce. And what is the advantage we have with that electromagnet means it is a controlled one. Why? Because by varying the current flowing through the coils, we can control the field density or the field intensity. Right? I hope this point is clear. But here, whatever the field we are trying to produce, rotating magnetic field we are going to produce, it is not with respect to a rotating core, rotating winding, but core is stationary, the windings are stationary, but the field has to be rotating. So how to produce a rotating magnetic field with a stationary winding and stationary core? We'll see, right? So here, rotating magnetic field, rotating magnetic field with stationary winding and stationary core, stationary core, stationary core. So before I try to explain this, see, whenever we talk about this magnetic circuit, I'll try to talk about electric circuit. Why? Because if you understand some concept from that, we can use the same concept here. See, I'm having a network with only one resistor, one resistor. So what I want to do means I want to pass current through this resistor. I want to pass current. So if I want to pass current, I need a driving force. So what is the driving force for the current? An EMF. An EMF. So you know the definition of EMF, it is electromotive force. So to make you understand between you and me, I'll just use one terminology, electron movement force. The force which is responsible to put the electrons in motion, which will result in current. But the true definition is electromotive force. I need one force. So you might have studied that what are the various sources of EMF are, which one can supply current means one is a battery. So if I connect a battery across that resistor, so the battery has the capacity to supply the current as it is a source of EMF. But what is the main problem we are having with a battery means it cannot supply the current to that particular load for an infinite time. It can supply only for finite time till that SOC big and state of that is the battery completely discharges. So it can supply only current for some time, right? So that is the reason the units of that battery is ampere hours. I can say this battery can supply this amount of current only for this amount of time. So that is the reason it is ampere hours. But if you want to have current for a longer time, then what I need to do, I need a coil, and coil should be moved under a magnetic field. Coil should be moved under a magnetic field. So if you just go into that generating station and if you just inquire about how that EMF is produced, means the engineer will tell you that. See, we'll be having a coils and those coils are continuously moved with the help of a prime mover in a magnetic field. So whenever those coils, or we call it as windings, are moved continuously in a magnetic field, then the flux linkages with that coils will change, or those conductors will be cutting the magnetic flux lines and an EMF will be induced in that. So whatever the EMF that is being induced will be collected and it will be transferred via the transmission line. And here we use that EMF to drive the current in our particular loads. So if that generator is rotating continuously, so whatever the current that circulates will be continuous and we can get the current for infinite time, right? So I can have this. So here, if I'm giving a DC, if the nature of that source is a DC or the magnitude of that voltage is fixed, so the current will be DC. So for a DC voltage, the current will be DC. For a AC voltage, the current will be AC. So can I say the nature of current, the nature of current depends on nature of EMF, nature of EMF. If that EMF is having a fixed value, then that current will be fixed. And if that EMF is having a, I mean to say, a alternating one, so that current will be alternating, right? Fine. See, why an EMF induction motor is a rotating transformer? Just hold, I'll tell. Why? Because in case of transformer, the secondary is a stationary, but here the transformer, the induction motor, the secondary is a rotating. Just Baba anonymous attendee, just hold for some time. Whatever the questions you have, slowly you'll get the answers, right? Please, right? Right, done. Yes, we can control the magnitude, you can see. So the nature of current depends upon the nature of EMF. Now, what is the analogy of current in a magnetic circuit? If you remember, what is the analogy of current in a magnetic circuit? Flux. Flux. So if you want to have a flux, then I need the driving force for that flux. So what is the driving force for the flux? MMF. Just like a EMF is the driving force for the current. So MMF, what is it? MMF, magnetomotive force. In other way, the force which is responsible to align all the dipoles. When all the dipoles are being aligned, then through that aligned dipoles, the magnetic flux lines will try to travel. So if you remember in my yesterday's class, if I'm taking a iron core and if I'm trying to place a north pole here, then all the dipoles will be aligned and the magnetic flux lines will be trying to travel along that aligned dipoles. The other possibility is the current carrying conductor. So what are the various sources we are having? One is a bar magnet. The other one is a current carrying coil. See, anonymous attendee. See, your questions are something like related, but just wait. Sir, by varying the speed of a bar magnet, can't we control the generated EMF? What do you mean by generated EMF? Or what do you mean by EMF? See, if I'm talking about a magnet, so when there is no coil, there is no concept of EMF. I'm talking with respect to that field. See, when that field is cutting the conductors, then definitely an EMF will be induced. Is it clear? But I'm not talking about EMF here as of now, anonymous attendee, right? So when the speed of the alternate that bar magnet is varied, the number of times the flux lines cuttings will vary, then EMF magnitude will vary. Is it clear, Baba? Anonymous attendee, is it clear? Right, Baba. Sirisha, sir, once again repeat. What you want me to repeat? Just a question type. Yeah. See, okay. So one request from other student. See, whatever the questions you have, my humble request to all. Whatever the questions you have, you write it on a paper and you ask me during question and answers. Why? Because few students are like getting interrupted with this, right? So you use this box only to communicate if there is some problem in that voice, audio struck or something else. So other than that, as of now, you don't use this box, question and answers box for this. So use this question and answers box when I'm discussing about the doubts. As of now, don't use this, please. Please don't use this, right? Please. Right. So I'll give time to write. Fine. Fine. So I'm closing that. See one thing. So if you are having any doubt with this audio, video, strucking, lagging, something, you intimate that to me. That's all. Nothing more is required. So one simple request to all. Simple request. If you are having any low voice, just raise the hands, all of you, once at a time. At least if I see 10, 20 people are raising the hand, I understood that there is some delay, right? Please do that. Fine. So if I want to produce a flux, I need the driving force. What is the driving force for the flux? EMF. So what are the various sources of MMF means? So we are having a permanent magnet which has the capacity to align all the dipoles, and the other one is a current carrying coil. So our intention as of now is to produce a magnetic field, that to rotating magnetic field. So if I want to produce a rotating magnetic field, I need the driving force. What is the driving force? A current carrying coil. So just like in case of your current, as current depends upon the nature of EMF, here the nature of flux depends upon the nature of MMF. If the nature of MMF is rotating, the flux will also rotate. If the nature of MMF is stationary, the flux will also remain stationary. So it will be along one axis. So here, so the nature of flux depends on nature of MMF. If MMF is stationary, flux is stationary, and if MMF is rotating, flux also rotate. Flux is also rotating. Flux is also rotating. Now what I'll try to do means, I'll try to take a stationary core and I'll try to take 3 windings and I'll try to pass 3 currents. And I'll see with those 3 windings and 3 current, what will be the nature of flux, nature of MMF. Why? Because winding and current will produces 1 MMF. Like how many windings we are trying to take? 3 windings. How many currents we are trying to take? 3 current. So how many individual MMFs will have? 3 individual MMFs will have. Then I'll find out the resultant of all those 3 individual MMF. If I'm successful in proving that the resultant of those 3 individual MMF is a rotating one, then I can blindly say that with those conditions, the field will be rotating, right? So first I'll be discussing how to produce a rotating magnetic field with the 3-phase windings and 3-phase currents. And yesterday I told you one thing, there is a difference between law and a theory. Law is always true. It doesn't need any mathematical proof. Why? Because it is based on the experimental demonstration or experimental proof. But whereas a theory may be true or a theory may be false. So if you want to say that your theory is correct, there has to be some mathematical proof for that. Then basing on that, we can say your theory is correct, right? So here we are discussing about rotating magnetic field. It is a theory. I say if you follow these conditions, then the field will be rotating. So no one has seen internally the field is rotating, but we feel the field is rotating, but no one has seen. We cannot see the field with your naked eyes as it is rotating. So for that, what I'm trying to do means I'm trying to take a mathematical proof for this. So using this mathematical proof, whatever the conditions I'm going to list out, with those conditions, the field will be rotating, right? So as it is a theory, I need to take up a mathematical proof also, right? So you may have doubt, sir, we are giving only gate examination. So in this gate examination, any mathematical proof will be asked. Obviously, there is no proof asked, but many times in your engineering service, in your gate, so whatever the discussions we have in the theory will be asked as a bits. So we'll see some important steps or important points in the theoretical proof. We'll see that, right? So first one is how to produce rotating magnetic field. Case one, rotating magnetic field, rotating magnetic field with three-phase windings, three-phase windings and a three-phase currents. Initially, how many windings we are taking? Three windings, three-phase windings and three-phase currents, three-phase currents, right? So these are the conditions. What are the conditions? We'll see. So here I'll write general requirements to be satisfied, to be satisfied to produce a rotating magnetic field. RMF means rotating magnetic field with three-phase winding and three-phase current, three-phase current, three-phase current, right? So what are the conditions I need to satisfy, right? See, the first point is whatever the three-phase windings you are taking, those three-phase windings should be physically placed with a space angle of 120 degrees. So all those three-phase windings should be physically placed with a space angle of 120 degrees. The first point is the three-phase windings, the three-phase windings, the three-phase windings should be physically placed, physically placed with a space angle of 120 degrees electrical, 120 degrees electrical, right? What do you mean by that? See, all of you, if I'm just considering a stator, so let us consider this is one phase and I'm having a winding on this axis. So these two are joined and this form one winding. So this is one winding, right? Right. So this is one axis. So with respect to this axis, after 120 degrees, so if I'm taking this one as 90, just roughly I'm drawing this. This is 90. So here I'll be taking one more, roughly here. Just 1 second. So this is one more phase B. Right. So this is one more phase. Then with respect to this, after 120 degrees, one more. So after 120 degrees, one more, one more. So this is something like this. So what has to be the space angle? So if I'm calling this one as a phase A with the terminals A dash. If I'm calling this one as phase B with the terminals B dash, and if I'm calling this one as phase C with the terminals C dash, then you can see if I'm calling this one as axis A, then if I'm calling this one as axis B, the angle between these two axes will be 120 degrees electrical. So the first point to be noted here is the angle between those three phase winding should be 120 degrees electrical, right? So let us consider in each phase the number of turns be n, 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 n. So the number of turns be n. So in each phase the number of turns be n. I hope this point is clear. So what has to be the space angle between each winding means it should be 120 degrees electrical, right? Then you may have a doubt, sir, you told that to produce a rotating magnetic field, the space angle between those three windings should be 120 degrees electrical. Yes. Sir, instead of maintaining 120 degrees, if I try to maintain, say, 100 degrees between A and B and 140 degrees between B and C, then 120 degrees between C and A. So in that case, we will not get rotating magnetic field now. We'll get. Problem is the speed, the magnitudes may not be same. What do you mean by placing that, right? If you remember in case of your, just see, if you remember in case of your synchronous machines, you might have drawn the placing of conductors. What is that? If I'm considering a single phase, say phase A with only one turn, so how many conductors are there? A dash. So I'm placing, so this is A conductor, this is A dash conductor. So here, this is your phase A. This is phase A axis. Phase A axis. Now let us consider the slot angle is, angle between the slots is something like 30 degrees. Let me consider 30 degrees. Then for 120 degrees, how many slots I need to place? 120 by 30, or let us go for 20. So that will be best. So the slot angle is 20. So 120 by 20 means how much it is? 6. Then if I want to place the conductors of phase B, so I have to, this is second slot, like that third slot, fourth slot, fifth slot, sixth slot, seventh slot. I need to place the conductors in the seventh slots. So with respect to this, so this is your phase B axis. Then angle between these two is something like 120 degrees, right? But instead of placing in the seventh slot, if I place the conductors in the sixth slot only like this, then this axis will be like this. Phase B axis will be like this, and angle between these two will not be 120 degrees, it will be less than 120 degrees. So in that case, is it possible to get a rotating magnetic field? The answer is yes. But when I'm talking about rotating magnetic field, please remember that at any instant of time, the magnitude should remain fixed. There should not be any change in the magnitude. What is the magnitude? We'll see. At the same time, the speed at which that field is rotating should remain fixed, constant. Then only I can say it is a rotating magnetic field. So if I'm having a rotating magnetic field with variable magnitudes and with variable speed, it may be rotating, but according to our requirement, we are not calling it as a rotating magnetic field. So if you want to have a constant magnitude and if you want to have a constant speed, then the first condition that need to be noted is the space angle between the two windings should be 120 degrees electrical. And the second point is the number of turns in each phase should be same. So as I have taken the number of turns are n, then the number of turns in all three phases should remain same. If n means 100 tons per phase, then A phase should have 100 tons, B phase should have 100 tons, C phase should have 100 tons. If the number of tons are not same, 100, 90, 80 like that, then obviously we will not get a constant magnitude. The magnitude may be vary. So if you want to have a constant magnitude and if you want a constant speed, the first point to be noted here is the space angle between the windings has to be 120 degrees electrical. The space angle between the windings has to be 120 degrees electrical with the same number of turns per phase. Is this point clear? Confirm me. Confirm me. Right. So I'll be drawing that here. If I'm calling this one as a phase A with the terminals A dash. So this is phase B with the terminals B dash, and this is phase C with the terminal C dash. This is the first point to be noted, right? So the space angle between the windings has to be 120 degrees electrical. So we measure the space angle with respect to their axis. So with respect to their axis. So what is the axis of phase A? So this is the axis of phase A. So with respect to that axis, it has to be 120 degrees. This is axis A, this is axis B, this is axis C. So the angle between those axes should be 120 degrees electrical, right? Done. The second point to be noted here is, C. As I told you that, we need to go for a mathematical proof. Why? Because it is a theory. So the theory need to be represented mathematically. Why? Because the theory, unless and until it is proved mathematically, I cannot trust or I cannot believe that theory. Why? Because theory may be true or theory may be false. So for that, I need to represent these three-phase windings mathematically. So for that, what I'm trying to do means I'm trying to define one angle called as theta, with respect to axis A. So I'm going to define one angle theta with respect to axis A. So this theta, I call it as space angle. Space angle. I call it as space angle, right? So how many turns are here? N turns, right? So I need to represent this phase A turns along this axis, So if you remember, if this is one vector and this is angle made by that vector with respect to this reference, so what is that component of that vector is A cos theta. Similarly, if N is the number of turns, then theta is the space angle. So what is the component of N on that? It is N cos theta. N cos theta. I hope this point is clear. All of you confirm me? All of you confirm me? Right. So if theta is equal to 0, so if theta is equal to 0 means which axis it is? It is A axis. So along A axis, you can find a coil with how many turns? N turns. Then if you just come here, so if this is theta, this is entire is 120, correct? Then what is this one? It is nothing but theta minus 120 or 120 minus theta, right? So can I represent phase A like this? Can I represent phase A like this? I can represent phase A as n cos theta. It is a mathematical representation of phase A. Mathematical representation. Mathematical representation. Just hold on. I'll explain. Mathematical representation of phase A. Of phase A. Phase A. So why I have to represent that phase A mathematically means, as I told you, that we need to go for a proof. What is that proof? Whatever the conditions we are listing out, what is that? The space angle between the windings has to be 120 degrees. Other windings or other conditions we tell with all these condition, whatever the field that is produced in the air gap is rotating. So I just with this condition, the field will be rotating. So tomorrow you may ask, sir, how can we trust you that with this condition the field will be rotating? So in that case, I can tell, see the mathematical proof. You check the correctness in that mathematical proof. If your mathematical proof is correct, if it is correct with respect to mathematics, then definitely it will be true with respect to the condition. So for that, I am trying to go for a mathematical proof. So how we are representing that phase A mathematically means n cos theta. So what is that theta? Theta is space angle or space displacement angle made with respect to A axis. A axis. So if theta is equal to 0, can you please tell if theta is equal to 0? So which axis it is? It is A axis. So along A axis, you can find a coil with how many turns? N turns. And if you want to find out how many turns are there along this axis, then I can say it is something like 60 degrees. If it is 60 degrees, then what is that? N cos 60 degrees. So what is the value of cos 60? It is 1 by 2. So n by 2. So it looks like when compared to your axis A, the axis which is making 60 degrees from A will have a turns equivalent to n by 2. Why? Because along axis A you can find n turns, but along that 60-degree axis you can find a coil with n by 2 turns. If I take 90 degrees, then you can assume that how many turns are there along that axis? There are no turns. Why? Because cos 90 will be 0. Like that, we can represent your phase A mathematically. Is this point clear? Confirm me, all of you. Is this point clear? Confirm me, all of you. Raise the hands. Right. Then once again, I'm reminding you, sir, what is the need to go for a mathematical proof, sir? As I told you that the reason for going for a mathematical proof is it is a theory, and this theory has to be proved mathematically. Then only we can trust the genuineness of this theory. So for that, we are going for the mathematical proof. So if A is n cos theta, then how to represent B phase? B phase. Then you please tell me in space, if you make 120 degrees, in space if you make 120 degrees, in space if you make 120 degrees, then where you are going to axis B. So from axis A, if you are making 120 degrees, you are going to axis B, right? So along axis B you can find a coil with n turns. Once again, if I'm taking axis A as a reference, so with respect to axis A, if I'm moving 120 degrees in space, if I'm moving 120 degrees in space, where I'm going to axis B. So along axis B, I can find one more coil, or I can find one more phase with how many turns? N turns. So can I represent phase B as N cos theta minus 120? So you can see if theta is equal to 120, so theta means what I told you, that theta is the angle made with respect to axis A. So with respect to axis A, if theta is becoming 120 degrees, so you are along which axis? B axis. So here you can see 120 minus 120 will be cos 0. Cos 0 is equal to how much? 1. Again, you can find out a coil with how many turns along B axis? N turns, right? Similarly, how to represent C phase? How to represent C phase? It is n cos theta minus 240. So if you are making 240 degrees in space, so theta becomes 240. So 240 means you are along C axis. So 240 minus 240 will be something like 0. Cos 0 will be 1. Again, you can find a coil with n turns along C axis. So these are the three mathematical representation of three phases, right? So once again, so in order to represent those three phase windings mathematically, just I'm defining one axis, making an angle theta with respect to A axis. So if n are the number of turns along A axis, then what will be the equivalent number of turns? What will be the equivalent number of turns along that axis? Means it is n cos theta. As theta increases, the number of turns along that axis will decrease, right? So I'm representing that axis like n cos theta. Similarly, how to represent B phase? It is n cos theta minus 120, and C phase n cos theta minus 240. Is this point clear? Confirm me. Confirm me, all of you. Represent, right? Done. So here n represent number of turns per phase, and theta represent space. So some textbooks call it as space displacement angle, or some textbooks they call it as space angle. So we are using theta. In some textbooks they use alpha. Why? Because please remember, no Greek letter has taken a patent that use that Greek letter only for that one. No. See, if I'm using theta, in our case, I'm calling it as a space angle. So if I go to electrical circuit, I'll use that theta for some power factor angle. In power electronics, I can use the theta for some angle, displacement angle. I can use. Nowadays, people are using these Greek letters for that coronavirus also, alpha, beta, gamma, theta, like that. So it is not like a universal patent that the theta has to be used only for power factor angle. I can use. So it is a space angle. In some textbooks, they use alpha to represent that space angle, right? So it is a space angle. The first condition is over. So tomorrow, if anyone questions you, Are Baba, you are on the way to produce a rotating magnetic field with three-phase windings and three-phase current. So what is the first condition I need to satisfy? Means I can say in the stator slots, see that those three-phase windings are physically placed with a space angle of 120 degrees. So they may ask me in back. So it is compulsory that the space angle has to be 120 degrees. If you are talking with respect to a constant magnitude and constant speed rotating magnetic field, then the space angle has to be 120 degrees for sure. Otherwise, you can have any other angle, right? Other thing is the number of turns per phase should be same. N should be same, right? Done. The second point is, the first point is over. The second point is I need to pass a three-phase current. So whenever I'm passing a three-phase current, the time angle between the currents has to be 120 degrees electrical. I need to pass a three-phase current with a time angle of 120 degrees, right? So the three phase currents which we are passing should have a time angle of 120 degrees. The three phase currents should have a time angle of 120 degrees electrical, right? See, whenever I'm talking about a three-phase current, please remember those three-phase currents should have some basic properties. What are those basic properties means? So I'm just drawing those three-phase currents. See, so morning only I have discussed synchronous machine for regular BTech students. Yes, I told them how to draw these three-phase currents. There also we need to discuss the rotating magnetic field, right? Just hold on. Right? So this is the three-phase current, right? So roughly I have drawn, please try to understand. So I'll make it. So this is one phase, red, yellow, and blue, RYB, general notations. Right. So these are the three-phase currents. I hope you understood. Please confirm me three-phase currents. Understood? Understood. So whenever I'm talking about the three-phase current, please remember one thing. What does that means? Those three-phase currents should be pure sinusoids. They should be pure sinusoids. That means the nature of those currents should be purely sinusoidal. That is the first thing. The second thing is the frequencies of those currents should be same. Frequency should be same. So if I'm talking about A phase current, IA, IB, IC, if the frequency of phase A is say 50 Hertz, frequency of B phase B should be 50 Hertz and IC should have 50 Hertz. The frequency should be same. Third and very important point is the time angle should be 120 degrees. The time angle should be 120 degrees. Time angle should be 120 degrees electrical. Generally, you know that we measure the time angle between the peaks. So generally, we measure the time angle between the peaks. If this is the peak and this is the peak, then angle in these two should be 120 degrees electrical. So if the angle between the peaks is 120 degrees electrical with respect to other instants of time, the time angle will be 120 degrees electrical for sure. So please remember, whenever I'm talking about the three-phase currents, so these 3 points should be kept in mind. What are those 3 points? The nature of those currents should be purely sinusoidal. The frequency should be same. the time angle should be 120 degrees, and one more point I forgot, the peak value should be same. The peak value should be same. So means all three phases should have the same peaks. Then you may have a doubt, sir, instead of 120 degrees time angle, if the time angle is other than that, is it possible to produce a rotating magnetic field? Yes. That the nature will be rotating, but it may not have a uniform speed, it may not have a constant magnitude, right? So if you want to have a constant magnitude, all these conditions has to be satisfied, right? Once again, the second point to be noted here is, what is that? So here the peak value should be same. Peak value should be same. Should be same. Should be same. Same. So this is the second point. What is that second point? The the three phase current should have a time angle of 120 degrees electrical. So what are those three phase currents we have drawn? And with respect to that, those currents should be purely sinusoidal. The frequency should be same. The time angle should be 120 degrees. The peak value should be same. And I told you one thing, we need to go for a mathematical proof. If I want to go for a mathematical proof, so these three currents should be represented mathematically. How to represent those three currents mathematically? See, I consider phase A. Just see, phase A I consider. Phase A I consider. This is phase A. This is Im. So I consider that this instant is omega t is equal to 0. At omega t is equal to 0, what is the value of current Ia? It is Im. So from this instant, when the time is increasing, then what happened to the peak value or the magnitude of that current decreasing? Then when omega t is equal to 90, please remember omega t is equal to 0 is the instant here, omega is equal to 90 is here. Then what happened to that current? 0. Then beyond that 90, what happened to that current magnitude? It is becoming negative. Then omega t, if it is 180 degrees, it is minus Im. Then if still it is increased, then you can see at 270 degrees, the current is becoming again 0. So this is Ia. Will agree with me? Please tell. Will agree with me? Please tell. Right. So can I represent your phase A current like this? Or Ia can I represent like this? Ia is equal to Im cos omega t. So please remember omega t is the instant at which the current is maximum. So if omega t is equal to 0, what is the value of Ia? So it is Im. So when omega t is increasing, what happened to the value of Ia? The magnitude is decreasing. So we can put that Ia mathematically like Im cos omega t. Similarly, how to present Ib? So Ib is equal to Im cos omega t minus 120. Why? Because when omega t is equal to 120, then you can see, so this is omega t is equal to 0. So omega t is equal to 120 means this state. At omega t is equal to 120, then which phase is having a peak value? B phase. So when omega t is equal to 120, so 120 minus 120 is 0. Cos 0 will be again 1. Again, what is the value of Im? What is the value of Ib? It is Im. Similarly, IC is equal to Im cos omega t minus 240. So like that, we can represent those three phase currents mathematically. So this is the mathematical representation of three phase currents. Representation of three phase currents. Three phase currents. Three phase currents. Once again, Baba, I need to represent three currents mathematically. For that, I have considered one instant time omega t is equal to 0. At omega t is equal to 0, which current is having a peak value? A phase. So with respect to that omega t is equal to 0, if that omega t is increasing, what happened to the value of that current? Decreasing. So I have represent those three phase currents like this, right? So here Im represent the peak value or the maximum value, and omega t represent the time angle. Represent the time angle. The time angle. Is this point clear? Confirm me all of you. Is this point clear? Confirm me all of you. Raise the hands. Please, all of you involve. I can see only few, right? Please. So two conditions are over. What are those two conditions? The space angle between the windings has to be 120 degrees. The time angle between the currents has to be 120 degrees. But if you just go back here, you can see each phase. Phase A is having two terminals, A dash. Phase B is having two terminals, B dash. And phase C is having two terminals, C dash. But how many currents are there? Only three currents. So altogether, how many terminals are there? Six terminals. But how many currents we are having? Three currents. So if I want to supply these three currents into those windings, I need to have only how many terminals? Three terminals. So here you can just go for, here you can see A dash is one set of terminals for phase A. B dash is one set, C dash is one set. Like that, how many terminals we are having? Six terminals. But how many currents we are having? Only three currents. Then if I want to supply those three currents into that three windings, I have to reduce those six terminals into three terminals. Then if I want to reduce those six terminals into three terminals, how to do? So we can go for joining the similar terminals or joining the dissimilar terminals. What do you mean by that? See, third point, I'm having phase A. What are the terminals of phase A? A dash. What are the terminals of phase B? B dash. What are the terminals of phase C? C dash. In this ABC, we call it as one set of similar terminals. We call it as starting terminals. Similar. So these are also similar terminals. Finishing terminals. Similar terminals. Starting terminals are AB terminals are A dash, dash, and dash. If I'm joining these similar terminals A dash, B dash, and C dash, then I can give one name to such connection. I can call this one as a star connection. Star connection. Star connection. So can I say like this? The three-phase windings are said to be connected in star if the similar terminals are joined together. So here, these are the starting ends. These are the finishing ends. I'm joining all the finished ends and I'm naming it as a star connection. Star connection. So is it clear? So Baba, this any strucking or anything is happening? Just raise the hand if it is no. If everything is correct, raise the hands. Right, done. So the three-phase windings are said to be connected in star if the similar terminals are joined together. Sir, we have learned something different for a star connection. You are just drawing it as a star connection. We have learned something different. What may be the something different? See, if I take those three-phase windings like this, A dash, B dash, C dash, and I'm joining all these similar terminals. Then even this I can call it as a star connection. Star connection. Sir, what is the difference between these two, sir? You said that star connection is basing on the joining of the similar ends. Absolutely correct. Then what is the difference between the first figure and the second figure? The first figure and second figure windings are connected in star only. There is no doubt in that. Absolutely, they are star connected. The only difference is the first picture represents that the angle between the windings is 0 degrees. That means all A, B, C are having a space time of 0 degrees. But in the second case, the axes are 120 degrees. It represents that the angle between the windings is 120 degrees. So here you can see this is your axis A, this is your axis B, this is your axis C. So what is the angle between those three axes? 0 degrees. They are parallel. But here if you look into this, this is axis A, this is axis B, this is axis C. What is the angle between these three? It is 120 degrees, right? So for defining star connection, it is not compulsory that the angle between those three windings should be 120 degrees. They may be 0 degrees, 10 degrees, 3 degrees, whatever the degrees it may be, they can be connected in star. So star connection means we talk with respect to that similar ends. That means if all the similar ends are joined together, then we can call it as a star connection, right? So the star connection may, the space angle may be 0 degrees or the space angle may be 120 degrees. It doesn't matter. So generally, we represent this type of star connection for rotating machines. Rotating machines. Why? Because in case of rotating machine, it is compulsion that the space angle between that should be 120 degrees. So here we represent this for a transformers. Why? Because in transformer, so the angle between the three phase windings is not 120 degrees, right? So can I say the three phase windings are said to be connected in star if the similar ends are joined together, right? See, the three phase windings, the three phase windings are said to be connected in star if the similar ends are joined together. Then what is the other possibility that the three phase windings can be joined means instead of joining the similar ends, I can join the dissimilar ends. What do you mean by that? See, I take those three phase windings A, A dash, B, B dash, this is C, C dash. You can see I'm joining this dissimilar ends. So this we call it as delta connection. So here also I can make it. See, don't worry, I'll just scroll down. You can take it. Just give me time. Let me complete this. A, A dash, B, B dash, C, C dash. So external angles are 120 degrees. So if the dissimilar ends are joined together, then what is the name given to such connection means it is a delta connection. So I think you understood. So basing on that space angles, we don't define star or delta. Basing on joining of similar ends, dissimilar ends, we define star or delta, right? So delta means the winding should be, the joining should be dissimilar ends. Star should be, the joining should be similar ends. I'll give a note here. What is that? The three phase windings, the three phase windings, three phase windings are said to be said to be connected in delta if the dissimilar ends are joined together, I hope this point is clear. Confirm me, all of you. Confirm me, all of you. All right. Then you may have a doubt. Sir, we agreed that the windings may be star or delta. We understood. Now to produce a rotating magnetic field, is there any compulsory that the winding should be star or delta? There is no compulsion. So the windings may be either star or the windings may be either delta, right? So can I say like that? To produce a rotating magnetic field, to produce a rotating magnetic field, produce a rotating magnetic field magnetic field, the three-phase windings can be connected either in star or delta. I hope this point is clear. Now let us go for our case. Here the windings are connected in star. So here the windings are connected in star. So here you can see A dash is joined with B dash. So this is A dash. I'm joining with a B dash. And this B dash is joined with C dash. So the windings are connected in star, but there is no compulsion that the winding should be star. So after that, what I'll try to do means I'll try to supply those three-phase currents into those three-phase windings. IA, I'm supplying here. IB, I'm supplying here. And IC, so IB is where it is, sorry. So IB, I'm supplying here. And IC, I'm supplying here. So how many individual MMFs will get here means we'll get 3 individual MMFs, right? So let me find out those individual MMFs. So what are those individual MMFs? So I'll find out the MMF due to phase A. So MMF means MMF. I'm using that F. MMF is nothing but N into I generally. So which N? So it is the mathematical representation of phase A. Which current? The current which we are passing through phase A. So what is the mathematical representation of your phase A? So it is N cos theta. And what is the current that we are passing? Im cos omega t. Im cos omega t. So here I can write it as Nim cos theta cos omega t. So here Nim I write it as some Fm into cos theta into cos omega t. So this is the MMF due to phase A winding and a phase A current. I should know the nature of this MMF. So what should be the nature of this MMF? This question was asked many times. What is the nature of that MMF due to individual windings and individual currents? It is a standing and pulsating MMF. So what is the meaning of standing and pulsating MMF? I'll explain this. Please see. So this is a very, very important. You find some theta here, some omega t here, something you find. Let me tell. See. So I consider on axis A. On axis A. On axis A, what will be the MMF here? It is Fm cos omega t. You can see it is Fm cos omega t. Why? Because on axis A, theta will be 0. So cos 0 will be 1. It is Fm cos omega t. I'll tell what is that. See, what I will do means, I'll consider one coil like this. Please tell. I'll consider one coil like this. Please tell. What is the nature of that MMF? Please understand this. I'll consider one coil like this. And through this coil, I'll be giving a DC. I'll be giving a DC. Let the number of turns be N and the value of this be IDC. So if anyone questions you, or what is the peak value of MMF, means the peak value of MMF will be N into IDC, and it will be along this axis. The strength will be N into IDC along that axis. So this is the axis of magnetic field. So what is the peak value means it is N into IDC. If I'm trying to indicate the current, it will be upward. So the strength will have N into IDC and it will be along that axis. Will agree with me? Will agree with me, all of you? So the peak value is N into IDC. So if I'm just imagining one axis here and I want to move 360 degrees in space. 360 degrees in space. So if I want to draw the magnitude of flux around that, So how to draw that? So with respect to space, if I want to draw that, if I'm calling this one as 0 degrees, here it is exactly perpendicular to that. The field will be 0. When you're moving to the 90 degrees, the field will be maximum. When you're coming to again 180 degrees, the field will be 0, 270 negative, again it is 0. So here, when I'm moving from this axis to 90 degrees axis, so what will be the field along this 90-degree axis? It is n into IDC. It is a peak value. When I'm moving away from that, as I'm moving away from that axis, what happened to the field strength? Decreases. Then when I'm exact at 180 degrees, the field strength will be 0. And when I'm just moving back again to 270 degrees, the field strength will be negative. Again, it will be 0 like this. So what is the nature of that MMF means? In space, it is a sinusoidally varying. It is a sinusoidally varying. And what is the peak value of that MMF means? The peak value of that MMF will be n into IDC, and that peak value will be along its own axis. Along its own axis, the peak value will be n into IDC. And if you are moving away from that axis, the magnitude will start decreasing. And when you are approaching the negative of that axis, the magnitude will be becoming minus n into IDC. Is this point clear? Confirm me. Confirm me, all of you. Right, done. Please see. Now what I will try to do means, instead of supplying that NIDC, what I will do means I'll take the same coil. I'll try to take the same coil, this one. I'll supply IDC by 2. IDC by 2. If my question is, what will be the peak value of flux or peak value of MMF means, I'll say NIDC by 2. And where the peak value will exist means the peak value will be along its own axis. It is NIDC by 2. So if I'm going to plot for this, so it will be NIDC by 2. NIDC by 2. Will agree with me? Will agree with me? Will agree? Raise the hands, all of you. Right. So the peak value will be NIDC by 2, and it will be maximum along its own axis. Now instead of that, if I supply NIDC by 4, then what happened? It will be like this. NIDC by 4 will be like this. So here what I'm trying to do means, I'm trying to vary the magnitude of current manually. I'm trying to vary the magnitude of current manually. When I'm trying to vary the magnitude of current manually, the peak value of that flux along that axis is decreasing. When the peak value was IDC, the peak value was IDC current. The peak value of MMF is NIDC. When the current is reduced to by 2, NIDC by 2. When current is reduced to by 4, NIDC by 4. When the magnitude of current is 0, then the flux will be 0. Flux will be 0. Now if I'm going to change the polarities like this, now I'm trying to supply IDC by 4, then it will be like this. When it is IDC by 2, it will be like this. When it is IDC again in negative direction, it will be like this. Will agree with me? Will agree with me? All of you tell me. So can I say the peak value will be pulsating along that axis. When the current is IDC, it is NIDC. When the current is IDC by 2, NIDC by 2. When current is IDC by 4, NIDC by 4. When current is 0, it is 0. When current is minus, it is going. So along the axis, the field is oscillating. The field is oscillating along its own axis with a peak value of NIDC and with a minimum value of 0 and with a negative peak of minus NIDC by 2. Will agree with me? Will agree with me? Will agree with me, all of you? Right. Now what I will try to do means, instead of varying the magnitudes of currents manually, what I will try to do means, I'll take the same coil, to the same coil, I'll give a AC now. Im cos omega t AC. So what is the difference between this circuit and this circuit? This current means in the first case, the magnitude of that current is manually varied, but in the second case, with respect to time, the magnitude of that current is varying automatically. When the magnitude of that current is varying automatically, then what is the peak value of flux here? It is NIM. When the current magnitude is Im, the peak value is NIM. But when the current magnitude is changing, then what happened to the magnitude of that flux? Decreasing. And it is oscillating along its own axis. It is oscillating along its own axis. So can I say like this? Can I say like this? In this case, you can see with the time, with the time, with the time, what happened to that flux? It will vary like this. It will be oscillating along this axis. It will be oscillating along this axis. Will agree with me? All of you, please tell me. So what is the nature of that MMF? What is the nature of that MMF due to phase A winding and phase A current? Means we can answer the nature of that MMF due to phase A winding and phase A current is standing. Means it is along only one axis. Which axis? A axis. It is oscillating along that axis with a peak value of n into Im with a minimum value of 0. So when the current flowing through that coil is Im, the flux along the MMF along that axis is n into Im. When the current magnitude is decreasing, the MMF value is decreasing. Along that same axis, it is decreasing, right? So if you want to know that along other axis, then it is n cos theta into Im cos omega t. So with respect to that theta, it is magnitude will be little bit less and it is oscillating along that axis. So can I say what is the nature of that MMF due to phase A winding and phase A current? Means I can say it is standing. Means standing means it is not standing up, and I'm talking about with respect to the same axis A, the amplitude is varying. So from NIM to minus NIM, it is oscillating along the same axis. So what is the nature of that MMF due to phase A winding and phase A current? Means it is stationary and oscillating. It is stationary and oscillating. Stationary and oscillating. Is this point clear? Confirm me all of you once. Right. So can I write? So the nature of MMF, the nature of MMF, the nature of MMF. See, once again, I'm repeating. I have taken a coil with N turns, right? And I'm passing a current of IDC. If anyone questions you, or what is the maximum value of MMF, I'll tell N into IDC. Or where you can find that MMF maximum along its own axis. Or what happened to that MMF along other than that axis, the value will be decreasing. You can see the value will decrease. Then if the current magnitude, if I'm changing manually, then what happened to the peak value of that MMF? Decreases. But it is oscillating, right? It is along that same axis. But if I want to draw that MMF along space 360, then it will be a sinusoidal variation, right? So instead of giving a DC and varying the magnitude of current manually, if I give AC, so what is the difference between AC and a DC? Means in DC, we are varying the magnitude of that current manually. But whereas in case of AC, that current magnitude is varying automatically with the time. When it is varying automatically with the time, what is the nature of that MMF? Means stationary and pulsating. So it will be stationary and pulsating along the same axis. Once it is NIM, 0 minus NIM, again 0, again NIM, it will be stationary and oscillating along the same axis. Stationary and oscillating along the same axis. Right. So can I say the nature of MMF, the nature of MMF due to phase A winding what is the charging? Oh, 15%. Phase A winding and phase A current. I'm not talking about this iPad. That laptop is 15%. Just the nature of MMF due to phase A winding and phase A current, that is IA, is stationary. I cannot call it as standing. Stationary, or in bracket standing, and pulsating MMF. Pulsating MMF. Right. Similarly, if I go for phase B, after how many degrees the phase B will be excited? 120 degrees. Again, that will be stationary and pulsating along which axis? B axis. So what will be the MMF due to phase B? I'm writing phase B. So it is N cos theta minus 120. What is the current which you are passing? Im cos omega t minus 120. Again, it is Nim cos theta minus 120 cos omega t minus 120. Again, it is Fm cos theta minus 120 cos omega t minus 120. So what the nature of this MMF means? Again, it is stationary and pulsating. Which axis? B axis. So if this is a B axis, so that MMF will be pulsating along this axis. So along this axis, it will be pulsating along this axis. Similarly, the MMF due to C phase will be pulsating along which axis? C axis. So how many individual MMFs will be having? 3 individual MMF, and those 3 individual MMF will be oscillating along those 3 axes with a peak value of N into Im. Right? Is this point clear? Confirm me, all of you. Confirm me, all of you. Right. So similarly, if I want to write phase C, I'm completing. Hope you can understand this. I'm writing directly. Fm cos theta minus 240 cos omega t minus 240. So I'm writing the nature of individual MMFs due to individual windings due to individual windings and individual currents are stationary and pulsating along their own axis with a peak value of N into Im. Is it clear? Confirm me, all of you. I have to have all should raise the hand. So nearly 400 plus are there. Please raise. Just give me 2 minutes time. Why? Because it is 10% showing there on the laptop. So it will be like again shut down otherwise. Just 2 minutes. Just be on. I'll come back. I have to search where is the charger. I'll come back. I could not find the charger. No, I got it. Okay. Right. So I'll give break after this. Don't worry. Right. So all are back. Raise the hands once if everyone is back. Right. So if I want to plot the MMFs, so these MMFs are like this. Right. So this is MMF due to phase A. This is MMF due to phase B. This is MMF due to phase C. This is the space. You can see if you go back here. So once again, all of you confirm with me. So voice, audio, the screen movement, all are correct. Right. Right. See, if you see here, so the peak value will be NIDC one axis, but if I want to draw with respect to space, it is sinusoidally varying. So here the peak value is AMMF, so it is FM along which axis? A axis. But with respect to space, that MM will vary. Similarly, what is the peak value due to phase B? It is FM along B phase. Similarly, it is due to C phase. Like that, we are having 3 MMFs, right? But see, we are not bothered about the individual MMFs. We are bothered about only the resultant MMF, right? So we are bothered only about the right. We are bothered about the. So once again, confirm me. So someone has. So you are able to hear me, all of you. Voice is clear. Raise the hands. The screen movement is clear. Once again, raise. Screen movement is clear. Right. Done. So now what I want to do means I want to find out the resultant MMF. If I want to find out the resultant MMF, what I need to do means I need to add up all individual MMF. Why? Because the nature of that field, rotating magnetic field, will be basing on the nature of resultant MMF. If I'm able to prove that if the resultant MMF is rotating, then the field in the air gap will also be rotating. So if I want to find out the resultant MMF, what I need to do means I need to add up all individual MMFs, right? So the resultant MMF FR is the MMF due to phase A, it is the MMF due to phase B, the MMF due to phase C. So what is MMF due to phase A? So it is FM cos theta cos omega t plus what is MMF due to phase B? FM cos theta minus 120 cos omega t minus 120 plus what is the phase C? FM cos theta minus 240 cos omega t minus 240. So if you observe carefully in all this, what is that I can take out common means it is FM. So it is cos theta cos omega t plus cos theta minus 120 cos omega t minus 120 plus cos theta minus 240 cos omega t minus 240. 240, right? Done. Now I need to simplify this. For this, I'll be bringing the trigonometric equations. What is that? You know that 2 cos A cos B is equal to cos of A minus B plus cos of A plus B. You may be knowing that. I'll throw these two down. If I throw these two down, what will be the answer? It is 1 by 2. It is 1 by 2. So if I'm going to compare the first one if I take cos theta cos omega t, then I can write this one as 1 by 2 cos theta minus omega t plus 1 by 2 cos theta plus omega t. Like that, if I'm going to expand the remaining this term and this term, and if I simplify this, the resultant will be like this. The resultant will be 3 by 2 times of Fm cos of theta minus omega t. This is the resultant due to all three phase. Now we need to decide what is the nature of this resultant. Nature of this resultant. You can see resultant is the function of space or the function of time. So this is a resultant MMF. So if I'm successful in proving that this resultant MMF is a rotating MMF, then the field which is produced by this MMF will also be rotating. Now I need to prove that this MMF is a rotating MMF, right? So once again, I'll go back, then we can see. See, our intention is we need to produce a rotating magnetic field with the three-phase windings and three-phase currents. What are the conditions I need to satisfy? Means the first point is the three-phase winding should be physically placed with a space angle of 120 degrees, right? We have shown what is called as 120 degrees. And mathematically, those three-phase windings are represented like n cos theta minus 120, theta minus 240, like that. Then I need three currents. What should be the nature of those three currents? Means those three currents should be purely sinusoidal. The peak value should be same. The frequency should be same. The time angle has to be 120 degrees. Then before we pass those three currents into those three windings, then those windings should be connected either in star or delta. Star means similar ends, delta means dissimilar ends. So to produce a rotating magnetic field, it is not like compulsory that the windings should be connected only in star. The windings can be connected in star or delta. So in our case, we have seen that the windings are connected only in star, but they can be connected in delta also. So when I pass those three currents into three windings, then we have seen that we had three individual MMFs. What are the nature of those three individual MMF? They are stationary and pulsating along their own axis with the peak values of N into Im. As the magnitude of those currents are changing, so those peak values also will changes along their own axis. But with respect to space, they are sinusoidally varying with a space angle of 120 degrees electrical. Is this point clear? Confirming? Confirming? But our intention is not to find out. Our intention is not to find out the individual MMF. Our intention is to find out the resultant MMF. Resultant MMF, right? So for that, I have added all the individual MMF, Then I got this one as a resultant MMF. But very unfortunately, you can see the resultant MMF is a function of two parameters or two scales. One is the space, the other one is a time. So, but here if you look into this board, the board is only a two-dimensional board. But on the same two-dimensional board, I have to represent the resultant with respect to time scale and with respect to the space scale. So how to do that? I'll do one thing. I'll consider omega t is equal to 0. When I consider omega t is equal to 0, you know that so which phase is having a peak value? Ia is having a peak value, right? Why? Because Im is that Ia is having a peak value of Im when omega t is equal to 0, right? Then what is the resultant? You can see resultant is equal to 3 by 2 times of Fm cos theta. Cos theta. Done. Then I'll take omega t is equal to 10 degrees. 10 degrees. Then what will be the resultant here? Resultant is equal to 3 by 2 times of Fm cos theta minus 10 degrees. I'll take similarly omega t is equal to something like 120 degrees. Then what is the resultant? It is equal to 3 by 2 times of Fm cos theta minus 120 degrees. I'll take omega t is equal to 240 degrees. Then what is the resultant? Means resultant is 3 by 2 times of Fm cos theta minus 240 degrees. So this is with respect to space, right? So before I plot that, I'll ask one thing. Please answer this. After this, I can plot this, right? Please see. See, someone is taking, I think you can take down. See, I'll give break at 7:15, 10 more minutes. Right, right. See, I'll do one thing. What does that means? See, right. I'll do one thing. What does that means? I'll take two voltages. You please tell me. I'll take two voltages, three voltages. I'll take V1 of t is equal to Vm sine omega t. So if I question you like this, or I'll be taking a time scale with respect to that time scale, what is the nature of that and what is the nature of that voltage? I can say the nature of that voltage is sinusoidally varying with a peak value of Vm when omega t is equal to 90 degrees. Will agree with me? Will agree with me, all of you? Please tell. Right. Now what I will do means I'll take another voltage V2 of t, which is Vm sine omega t minus 10 degrees. If I question like this, what is the nature of that voltage with respect to time means, then we can see the nature of that voltage with respect to time is again sinusoidally varying, but the peak value shifted. The peak value shifted by 10 degrees. The peak value shifted by 10 degrees. Will agree with me? The peak value shifted by 10 degrees in space. Will agree with me? Like that, if I take another voltage V3 of t, which is Vm sine omega t minus 90, then the nature of that voltage with respect to time scale is sinusoidally varying, but the peak value shifted by how many degrees? 90 degrees in time. Will agree with me? Please tell me. Tell me. Right. Now, if anyone questions you, or what is the nature of this resultant voltage with respect to the space, then you can see theta is the space angle. So with respect to space, what is the nature of that MMF wave means? It is sinusoidally or co-sinusoidally varying. What is the peak value? It is 3 by 2 times of Fm. So if I want to plot the resultant with respect to space angle, just give me 1 minute. So what is the nature of that MMF with respect to space? Means it is sinusoidally varying. So you can see here, this axis I'm taking it as a space axis, so space angle. So here, what is this angle and what is the scale? Time scale. So what is the scale I'm taking here? Space. So the resultant. So what is the nature? So when omega t is equal to 0, the peak value is how much? 3 by 2 times of Fm. When theta is equal to 0, it is Fm. So this is theta is equal to 0. theta is equal to say 120, say this is theta is equal to say 240. So here it is like this. Drawing, just give me time. So this is when omega t is equal to 0 and theta is equal to 0. So when omega t is equal to 0, theta is equal to 0, what is the value of this? It is 3 by 2 times of Fn. Now with respect to time, what happened to the resultant wave? It is shifting. Shifting. You can see. So with respect to space, it is sinusoidally varying. With respect to time, it is shifting. Just you go back to this. So you can see voltages with respect to time, they are sinusoidally varying, but they are shifted with some angle. So here also, what is the x-axis here? The theta and the space angle. So with respect to space, they are sinusoidally varying resultant, but with respect to time, it is shifting. The peak value is shifting. So here, the peak value is shifting like this. It is shifting like this. In other way, I can say it is traveling from axis to axis. So this is a resultant wave which is shifting. So this is for omega t is equal to some 10 degrees, like that it is shifting from axis to axis like this. It is moving. So one thing to be noted here is with respect to space, what is the nature of the resultant wave? Means it is sinusoidal varying. Just like you can see in case of this, please try to understand. In case of this, the peak value will be always n into ITC along axis A. And with respect to space, what happened to the nature of that MMF? It is sinusoidally varying. But what is a good thing in case of this resultant MMF means with respect to space, it is sinusoidally varying, but the peak value is not remaining. The peak value is not remaining along the same axis. With respect to time, the peak value is also moving. It is also moving in space. So it is moving in space. The peak value is also moving in space. But here, in case of single phase, the peak value is only NIDC. It is existing along one axis. But with respect to space, the magnitude is decreasing. But here, with respect to space, it is sinusoidally varying. But with respect to time, the peak value is moving. So 2 points you have to note. One thing is, with respect to space, what is the nature of the resultant MMF? Sinusoidally varying. So when the excitation is given to phase A, and if you're talking about along A axis, what is the peak value? It is 3 by 2 times of Fm. So will the resultant stand there only? No, with respect to time, the resultant will be moving from axis to axis and it is moving along the space. 360 degree it is moving. So it is moving throughout the space. Is this point clear? Still, I'll explain this by taking a graphical representation. Don't worry, right? First point is, what about the nature of that individual MMF? The nature of that individual MMFs are standing and pulsating. Please try to remember, I'm using one terminology, standing. So with respect to time, they are standing along their own axis. They are remaining there only. But with respect to time, their magnitudes are changing. Why? Because the magnitude of the currents are changing, the magnitudes of the peak values are changing. It is standing along the same axis. But what happened to the resultant? With respect to space, it is sinusoidally varying, but the peak value is not remaining along the same axis. With respect to time, the peak value is moving. It is moving. So it is moving throughout the 360 degrees. So what is the nature of the resultant MMF means? With respect to time, the peak value is not standing, the peak value is moving. You can see the peak value is moving. So theta is equal to 0. So it is theta is equal to some 10. The peak value is moving. The peak value is moving with the time. But in case of individual MMF, the peak value is remaining stationary. It is standing there itself, but the peak value is moving here. As the peak value is moving, what the nature of the resultant MMF means? The nature of the resultant MMF is rotating. So the nature of that individual MMF with respect to time, it is standing. It is along only one axis. But what is the magnitude of the individual MMF? It is pulsating. But what is the nature of the resultant MMF with respect to time? It is moving. When I'm using the term standing in for individual, for resultant, I'm using the terminology moving. It is moving. But what is the peak value? The peak value is remaining same, 3 by 2 times of Fm. It is remaining same with respect to time, and it is moving throughout the axis. Is this point here confirm? Confirm? Right. So tomorrow, if anyone questions you, questions you, questions you, or can you please list out some differences between individual MMFs and resultant MMF? Yes. I'll say the individual MMF is a standing MMF, stationary MMF. That means it will be only along the same axis, along the same axis. The second point is the magnitude of that individual MMF will be varying. So NIM, when the peak value is IM, when the peak value or the current flowing through that current phase is decreasing, that magnitude is decreasing. So with respect to time, the magnitude of that individual MMF is changing. With respect to time, the magnitude of that individual MMF is changing. Then what is the nature of that MMF with respect to space? It is sinusoidally varying with a peak value of NIM along axis A, right? Then with respect to the resultant, what is the nature of the resultant MMF? With respect to space, it is sinusoidally varying, agreed. But with respect to time, the peak value is remaining fixed. Fixed. How much it is remaining fixed? 3 by 2 times of Fm. And with respect to time, it is not lying along the same axis, it is moving throughout the space. So the individual MMF is a stationary standing MMF, the resultant MMF is a moving MMF. The magnitude of individual MMF will be varying, the magnitude of the resultant MMF will remain fixed. Is this point clear? Confirm me. Right. Still, graphically, I'll explain. Don't worry. Still, as it is 7:15, still it is not over. So some people may have some confusions. So if I go for the next way of explanation, you can make the things clear. See, I'll tell you one thing. Recently, if I'm correct, 2019, I think. So one of the student in one of the PSUs, he was asked to explain the concept of rotating magnetic field on the board. See, most of the people think that just scoring in gate is enough. Of course, in 90 to 95 PSUs, it is enough. But if those people want to see your communication and convincing skills, so nowadays they are asking you to go and present on the board. So please remember that it is not like a luck you are getting the score. It is something like your hard work. You have to just learn the basics and get the things done. Is this clear? Confirm all of you. We'll see. Take the break. Right. See, it is 20 to 25 minutes break roughly, right? I'll come back after the break and we'll finish this, right? Thank you. Right. We'll start the class. So all of you confirm me whether you are clear with my voice, audio, and the streaming of the screen. So I think it is synchronized. Right. Done. So before I proceed with, so let me bring the differences between the individual MMF and the rotating MMF, the resultant MMF. Individual MMF is the standing MMF with a variable amplitude along the axis, but whereas the resultant MMF is a rotating MMF with a fixed amplitude of 3 by 2 times of Fm, and it is moving in space, right? So finally, can I conclude basing on this analysis, the resultant MMF is a rotating MMF, right? Still, with the help of some analysis, I can prove. You can see here. So these are the three individual MMFs: FA, FB, FC, right? So I'll represent those three instantaneous MMFs with a phasor. So this is FA with a peak value of Fm, and with respect to this is FB with a peak value of Fm. Why? Because after A phase, B phase will be excited after 120 degrees. This is FB, FC with a peak value of Fm, right? Now I need to find out the resultant. So I want to find out what is the resultant MMF at any instant of time or at any point. See, if I take this, I consider this one as some instant of time. At this instant of time, we can see I need to find out the MMF due to phase A, I need to find out the MMF due to phase B, and I need to find out the MMF due to phase C. Let me call at an instant of time T1. So what is the instant of time T1? The MMF due to phase A is Fm, hence it is Fm. The MMF due to phase B will be minus Fm by 2, and the phase C is also minus Fm by 2. I need to add up all these three individual MMF vectorially. If I'm adding up, you can see. So this is Fm. Please understand. This is Fm. This is Fm, right? And minus Fm. B phase is minus Fm by 2. So it is Fm by 2 along negative axis, and C phase is also Fm by 2 along negative axis of C phase. Fm by 2 along negative axis. Now I need to find out the resultant along this axis. So what is the resultant? So this is something like 60 degrees, and this is 120 degrees, and this is 60 degrees, and this is also 60 degrees. So what is the component of this Fm by 2 onto this axis? It is Fm by 2 cos 60, and what is the component of this here? It is also Fm by 2 cos 60. Then what is the total resultant now? It is Fm plus 2 into Fm by 2 cos 60. So here 2 will get cancelled. Then Fm plus Fm by 2, Fm cos 60, it is 1 by 2. So it is how much? 1 by 2 times of Fm. So if I'm trying to draw a circle here, so if I'm calling this one as A axis, this is B axis, and this is C axis. A, B, C. Then what is the amplitude at that instant of time? The amplitude at that instant of time is 1.5 times of Fm along axis A. Is it clear? You can see here. So these are the individual MMS with the peak values of Fm, which are sinusoidally varying in space. I need to find out the resultant. Resultant is nothing but the sum of all individual MMS. Now I consider another instant of time. This is T2. At T2, you can see the MMF due to phase A is Fm by 2. The MMF due to phase B is also Fm by 2. But the MMF due to phase C is minus minus Fm. So if I find out the resultant, then the same logic you can apply. So the resultant MMF will shift from here to here, somewhere here. Like that, if you are going to find out the resultant MMF at every instant of time, then you can see the resultant MMF will be moving in space. Moving in space with a peak value of how much? 1 by 2 times of Fm. 1 by 5 times of Fm, or 3 by 2 times of Fm, right? So finally, what is the conclusion we can see? Basing on these drawings, I can conclude that the resultant MMF is not stationary, just like your individual MMF, it is not standing. So with respect to time, the resultant MMF is moving in space. Moving in space. And one more good thing here with the resultant MMF is, unlike your individual MMF, the amplitude is not, or the magnitude is not changing with the time. Here, the magnitude is remaining with the time. So with the time, the magnitude is remaining same, and this resultant MMF is moving. So that's the reason I used one terminology. The individual MMF is standing, but whereas the resultant MMF is moving, it is rotating, right? So I hope this is clear. Confirm me all of you. Confirm me all of you. Right. So one more thing, finally I conclude. So this will give a clarity. Finally, I'll conclude this. See, if I take the resultant MMF FR 3 by 2 times of Fm cos theta minus omega t. This is the resultant MMF. See, so I consider omega t is equal to 0. So what is the meaning of omega t is equal to 0? It is the instant of time when the Ia is having a peak value of Im. So Ia is having a peak value of Im. Then I'll take theta is equal to 0. So theta is equal to 0 means which axis here? It is A axis. Then what is the resultant MMF here? It is 3 by 2 times of Fm. Along which axis? It is along A axis. Along A axis. Along A axis. Then I'll take omega t is equal to 120 degrees. Omega t is equal to 120 degrees means this peak value Im is going to which phase? Ib. So now Ib is having a peak value. Now I'll take theta is equal to 120. That means along which axis it is? B axis. So FR2 if I take, again it is 3 by 2 times of Fm, again 0. The peak value will be 3 by 2 times of Fm. Like this, if I take omega t is equal to 240, then theta is equal to 240, then the resultant will be 3 by 2 times of Fm. 240 means which axis it is? C axis. It is like this. C axis like this. Then, so what is that? What is this observation C? So please try to understand. When omega t is equal to 0, the excitation is given to phase A, and that phase A winding is along axis A, on axis A. So what is the resultant? The resultant is 3 by 2 times of Fm along axis A. When I'm talking omega t is equal to 120 degrees, the excitation is to phase B with a peak value of Im, and that current is flowing through B phase, and B phase is along which axis? B axis. So this resultant is shifting to B phase. Similarly, at omega t is equal to 240, which current is having the peak value? C phase, and C phase is along which axis? C axis. The resultant is moving to C phase. So can I say like this? With the time, I'll write the statement. With the time, the peak value is moving from phase to phase. When omega t is equal to 0 degrees, the peak value Im is for phase A and the resultant is along A axis. And after 120 degrees, the peak value is shifting to phase B and it is along B axis. The resultant is shifted to B axis. Similarly, at omega t is equal to 240, the peak value is for phase C. The phase C is along C axis. So what is that observation? When omega t is equal to 0, we are giving excitation to phase A. Where is that phase A located? The phase A is on A axis. After 120 degrees, the excitation is given to which phase? Phase B. Then phase B is along which axis? B axis. So it is B axis. Like that phase C, C axis. So what is the relation? So when omega t is equal to 0, then the excitation is to phase A axis. When omega t is equal to 120, the excitation is given to phase B axis, that is phase B winding. When omega t is equal to 240, the excitation is given to phase C axis. So what is the relation you are finding between A and B phases means the relation is directly proportional. So what is the relation you are having between theta and omega t means it is directly proportional. What is the meaning of that? See, when omega t is equal to 0, the excitation is given to A phase. When omega t is becoming 1 degrees, the theta is also becoming 1 degrees. When omega t is becoming 1, theta is becoming 1. What happened to the resultant? Resultant is 3 by 2 times of Fm cos 1 minus 1. So again, what is the value? 3 by 2 times of Fm. Along which axis? 1 degree axis. When omega t is becoming 2 degrees, theta also becomes 2. It is 2 degree. When omega t is equal to 3, like this, with omega t, which value is changing internally, theta is changing. With both omega t and theta, what happened to the position of the resultant vector? It is moving in space. So when it is moving in space, the peak value or the amplitude is not changing. The peak value is remaining same. So with all this example, with all this conclusion, I can say that the nature of the resultant MMF produced by those three individual MMFs is a rotating MMF. So I'm not saying that it is standing along one axis with the time. With the time, it is moving from axis to axis. As it is moving from axis to axis, I can conclude that the nature of the resultant MMF is a rotating MMF. Rotating MMF. Is this point clear? Confirm me, all of you. Right. So if anyone questions you, Are Baba, can you please prove that the nature of the resultant MMF with the three-phase windings and three-phase current is rotating? Yes. So in that case, whatever the mathematical equations we have taken, you have to take, and finally you have to prove all these things. Then you can see here, you have to prove this. So in the coming days, whenever you are coming across this cos theta minus omega t term, so this cos theta minus omega t term represent a rotating MMF, and its coefficient represent the magnitude or the peak value, magnitude or the peak value, right? So you can see the resultant MMF is rotating. So with the time, the what happened to that MMF? It is moving. So one second, some questions people are throwing. Yes, in all cases, omega t is equal to theta, absolutely. Why? Because both are linearly related. With omega t, theta will be changing. With both omega t and theta, the resultant MMF is smoothly rotating in space with the same peak value of 3 by 2 times of Fm. Is it clear, anonymous attendee? Is it clear? Are Baba Dinesh, here the windings is rotating or static? Baba, I told you that windings are stationary. Right, done. So finally, so I can say the nature of the resultant MMF is a rotating MMF. Now the question comes, when it is rotating, then with what speed it is rotating? So which parameter decides the speed of the rotating magnetic field? We'll see. And you know that distance by time is the speed. So the spatial distance by time is your omega. So what is the relation we are having between theta electrical and theta mechanical is P by 2. Don't ask now, your DC machine or synchronous machine teacher will explain, right? What is the relation? Theta electrical and theta mechanical is represented with P by 2, related with. So here I'll differentiate with respect to time. If I differentiate with respect to time, so this is omega electrical is equal to P by 2 times of omega mechanical. So what is that omega electrical? 2 pi f is equal to P by 2, 2 pi n by 60. So here 2 pi gets cancelled, and that speed is given by 120 into f by p rpm. Why? Because here n is the rpms. So this is speed, we call it as a synchronous speed. So this is speed, we call it as a synchronous speed. So what is the speed at which that field will be rotating, or the resultant MMF is rotating, means this is called as synchronous speed. Synchronous speed. Synchronous speed. So how to write that synchronous speed in RPS? Revolutions per second. It is 120 into F by P by 60. 2, it is F by P by 2 RPS. Right? So finally, can I conclude like this? Whenever the three-phase supply or the three-phase currents are allowed to pass through the three-phase winding. See, as of now, whenever I'm using this terminology, three-phase currents, please remember that the nature of those three-phase currents are purely sinusoidal. The peak values are same. The time angle between them is 120 degrees and the frequencies are same. So I'm not going to repeat every time all these terminologies. And when I'm talking about three-phase windings, please remember that the number of turns are same. The space angle between the are 120 degrees electrical. So I'll give the statement, please see here. Whenever the three-phase currents, I'm not giving all the list outs. Three-phase currents are allowed to flow through the three-phase windings, then there are three individual MMFs which are stationary. Instead of using the term stationary, I use standing. Stationary or standing, pulsating MMFs with the peak values of FM. FM is N into IM along their own axis, and the resultant of all those three individual MMFs is a rotating MMF given by, what is the rotating MMF? Already we have seen, FR theta comma T is equal to 3 by 2 times of Fm cos theta minus omega T, which has an amplitude three by two times of Fm, and which rotates with a peak value of rotates not peak value, which rotates with a speed given by ns is equal to 120 into f by p, called synchronous speed. Synchronous speed. As the nature of resultant MMF is rotating the flux produced by such rotating MMFs is also rotating, and such fields are called rotating magnetic fields. So this is something about rotating magnetic fields. Please confirm me, all of you, if you understood. Raise the hands once. All right. Now let us see some observations. Very, very important observations. Some observations. See one thing. Even if I am writing on a blackboard, your PDF will be white. You can see this white color will be turning into black, and the remaining color will remain the same thing, right? So if you want to just check, I'll show. Just 1 second. Like this it will look, right? Your PDF will be like this, don't worry. Right. Is it clear? So most of the people are having a doubt whether in which color it will be. Don't worry. Observation. So what is the magnitude here? So magnitude is 3 by 2 times of Fm. So it is 3 by 2 times of N into Im. So it is 3 into 1 by 2 into N into Im. So in this, 3 represent number of phases. Number of phases are the number of windings. So here, how many windings we are using on the stator? 3 windings. Then the magnitude will be 3 by 2 times of N into Im. So tomorrow, if you are increasing the number of windings to say 5, then it will be 5 by 2 times of N into Im. So with the increase in number of phases, number of windings, the magnitude, the strength of the field will increase, right? So can I say with the increase in number of windings, number of phases, the magnitude of resultant MMF will increase. So that is the reason when compared to a single phase, the 3-phase induction motor will be having more torques. Why? Because the strength will be more. The other one is ns, the speed at which it will rotate. It is f by p by 2. Then you can see in this there is no like 3 term. So when there is no 3 term, so it is independent of number of phases. That means even if I am placing 3 windings, the speed will be ns. Even if I am placing 5 winding, the speed will be ns. Even if I am placing 100 winding, the speed will be ns. So the speed of the rotating magnetic field is not dependent on number of phases. right? So it may be 3 phase, 100 phases, the speed will remain same, right? The speed of rotating magnetic field is independent of number of phases. So this is something about your rotating magnetic field. Please confirm me, all of you. If it is clear, confirm me. Right. So tomorrow in our coming classes, we are going to see that even the rotor of an induction motor will also rotate in the same direction as the field. If I'm assuming that in this case, the rotor is rotating clockwise direction, so the field is rotating clockwise direction, in which direction the rotor will also rotate? The rotor will also rotate in clockwise direction only. So if you want to reverse the direction of the rotor, then what you need to do means you need to change the direction of rotating magnetic field. So if you want to change the direction of the rotating magnetic field, what you need to do? Just I'll give some important steps. Then after that we can discuss. So conditions to reverse the direction of rotating magnetic field. So what I will do means I'll take these three-phase windings. I'm not drawing all the picture again, so you understood that. Right? So this is n cos n, n, n. So here what I'm trying to do means, so through this phase A, I call this one as A phase, this B phase, this C phase. So through this phase A, I'll be supplying IA current. Through phase B, I'll be supplying IC current. And through phase C, I'll be supplying IB current. So you can see the currents in these two phases are changed. So previously, what was the current in phase B, IB? Now what is the current I am passing? IC. Previously, what was the current in phase C, IC? I'm passing IB. So the currents in two phases I'm changing. If I'm changing the currents in two phases, what is the individual MMF? It is, I'm writing directly, Fm cos theta cos omega t. Then what will be that FB? So it is Fm cos theta minus 120, but which current we are passing there? C phase current. So the C phase current is represented with omega t minus 240. Similarly, phase C, Fm cos t theta minus 240 cos omega t minus 120. Why? Because in C phase, which current we are passing? B current. Then if I am finding out the resultant, so it is Fm cos theta cos omega t plus cos theta minus 120 cos omega t minus 240 plus cos theta minus 240 cos omega t minus 120. So if I simplify that, this will be 3 by 2 times of Fm. So cos theta plus omega t. So it is theta plus omega t. So if it is theta plus omega t, what do you mean by that? Means, so instead of this resultant MMF traveling in positive theta, instead of this is a positive theta. So omega t, this is theta minus omega t. So this is positive theta. Now, as the currents in two phases are changed, so this resultant MMF will be traveling in the negative theta direction. So it will be traveling in negative theta direction. Like this, it will go back to negative theta. Negative theta means the phasor will be moving like this. If I'm taking the forward move as a positive forward direction, this negative I take it as a backward direction. So can I say I'm not taking the full theoretical proof for this? I'm trying to give one statement. What is that? If you want to change the direction of the rotating magnetic field, see that the currents in any two phases you are changing. So previously current in phase B was IB, now we are changing it to IC. Similarly, the current in phase C was IC, now we are changing it to IB. So when you are changing the currents in two phases, then the direction of the field will be reverse, right? So can I give a statement here? To reverse, to reverse, to reverse the direction of the rotating magnetic field, direction of the rotating magnetic field, rotating magnetic field, change the currents, currents in any two phases, any two phases, right? So just I'll show it like graphically. What is that we are trying to do? See, graphically, please understand this. So let me consider this is a three-phase induction motor with the stator windings connected in star, and with those three terminals are brought out, ABC. And I'm having three-phase currents with a time angle of 120 degrees with a phase sequence of ABC. What is the meaning of phase sequence of ABC? Means among IA, IB, IC, which peak is coming first means IA current, followed by IB current, followed by IC current. So what is the definition for that phase sequence? Means it is the order by which the respective peak values of those phases are coming in sequence. ABC means among IA, IB, IC, which phase current is having first peak value? IA, followed by IB, followed by IC. So first IA phase is coming, peak, IB, then IC. I think this point is clear. Understood all of you? Raise the hands. Right. So here what I'm trying to do means I'm trying to give this IA to phase A, IB to phase B, and IC to phase C. So what is the meaning of that? So among A, B, C, so which phase is excited with peak value first? A phase, followed by B phase, followed by C phase. So if I'm trying to show the same thing here, so first this is A phase, B phase, C phase. First, which phase is excited with peak? A, after that B, after that C, after that C. So I'm representing IA, IB, IC. First, which phase? A phase, followed by B phase, followed by C phase. No, 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 sir. What I will try to do means, what I'll try to do means, I'll try to first give IA to this phase B, IB to phase C, IC to phase A. That means I'm changing this. So IA I'm passing it to which phase? B, followed by C, followed by A, or C, A, B. So in all these cases, so here first which phase is excited? B phase, followed by C phase, followed by A phase. Even in that case also, what is the direction of the field? Clockwise. So can I say, if your phase sequence is either ABC or BCA or CAB, in all the cases, what will be the direction of the field? Same. Why? Because ABC, BCA, CAB will have the same phase sequence. What is the meaning of phase sequence? Pumping the peak values in the respective phases. First, in which phase you are pumping the peak value? A phase. After that, in which case? B phase. After that, in which case? C phase. BCA means which phase is having a peak value first? B phase, followed by C phase, followed by A phase. Then in all the cases, what will be the direction of the field? Clockwise. Is this point clear? Confirm me. Is this point clear? Confirm me. In this all cases, clockwise. Now what I'm trying to do means I'm trying to change the currents in two phases. I'm trying to change the currents in two phases. If I try to change the currents in two phases, what happens? Let us see. I'll take the same motor A, B, C. This is IA, this is IB, IC. So here IA, IB means first is A phase, IA, IB, IC. But here what I'm trying to do, first A phase is excited with IA, but IB is excited with C phase like this. So here if I try to draw this A, B, C. First, which phase is excited here with peak value? A phase. After that, which phase is excited with peak value? C phase. After that, which phase is excited? B phase. Then in this case, what will be the direction of the field? Reverse. Reverse. So can I say like this? When you are changing the currents in two phases, you are changing the phase sequence. What is the meaning of phase sequence? The order by which the respective peak values are flowing in the phases are changed. So first is ABC. First IM is that IM is in phase A first, followed by B phase, followed by C phase. Now in this case, first in which phase that your peak value is having? A phase, followed by C phase, followed by A phase. So here if I'm trying to draw this IA, IB, IC. So here A, C, B or C, B, A or B, A, C. In this case, what will be the direction of the field? It will be counterclockwise direction. So I hope you understood this. So tomorrow, if anyone questions you, Are Baba, can you please explain me how to change the direction of the field? Then you can say by changing the currents in two phases, by changing the currents in two phases, the phase sequence is changed. So whenever the phase sequence is changed, the direction of the field will be reverse. There is no doubt in that. So can I change? So already here we have given to reverse the direction of the rotating magnetic field, change the currents in two phases. So is it compulsory that always we need to change in AB or BC? No, any two phases you can change. Then you may have a doubt, sir, if I change the currents in all three phases, what happens? If all three phases, you can see here, IA is passed into B phase, IB is passed into C phase, and IC is passed into A phase. So it is something like BCA. When it is BCA, the phase sequence will remain same, the direction of the field will remain same, right? So this is something about a rotating magnetic field with the three-phase windings and three-phase current. Let me once again give a summary, right? So if anyone questions you, Arababa, can you please list out the conditions to produce a rotating magnetic field with the three-phase windings and three-phase current? Yes. What are those conditions? The first condition is those three-phase windings should be physically placed with a space angle of 120 degrees electrical. Those three-phase current should have a time angle of 120 degrees electrical. So before we pass those three currents into the respective three windings, so those three-phase windings can be connected either in star or delta. Star means the similar ends, delta means the dissimilar ends. But to produce the rotating magnetic field, the three-phase windings can be connected either in star or delta. Absolutely, we don't have any issue in that. So when I pass those three windings and when I pass those three currents into three winding, I have three individual MMFs which are stationary and pulsating along their own axis, and they are sinusoidally varying in space with a time angle of space angle of 120 degrees. But when I'm talking about the resultant of all these three individual MMF, the resultant MMF is a rotating MMF with a peak value of 3 by 2 times of Fm, and which is moving in space. So with what speed it will be moving in space means it is moving with a speed of 120 into F by P RPM or F by P by 2 RPS. So this is something like this. So if anyone questions you, Are Baba, can you please explain how to reverse the direction of the rotating magnetic field means, then you can say by changing the currents in two phases. Or what is that you are trying to do by changing the currents in two phases means, you can say by changing the currents in two phases, the phase sequence is changed. So what is the meaning of phase sequence? Means it is the order by which the respective peak values are changing. So A, B, C means first in A phase the peak value is coming, next is B phase, next is C phase. So if it is A, B, C, the direction if it is clockwise, if I'm giving A, C, B, the direction will be counterclockwise direction, right? So this is something about a rotating magnetic field. In one of the gate examination, there was a question asked, if ABC phase sequence, if ABC phase sequence gives a clockwise rotation, just I'm giving a bit, clockwise rotation, what has to be the phase sequence for a counterclockwise rotation? What has to be the phase sequence for a counterclockwise rotation? Answer is BCA, option B, CAB, option D, ACB, option D, either A or B. A or B. What is the answer? Can you please type it in the box? It is C. Very good. So it is ACB. Correct. It is C. So the answer is C. So this is something about your rotating magnetic field. Then you may ask me, sir, you told that the magnitude of this rotating magnetic field depends upon the number of phases. If I'm designing an induction motor with 5 phases, so can you please tell me what are the conditions to produce a rotating magnetic field with 5 phases? Yes, I'll tell. So like this, I can answer for 5 phases today. Then tomorrow one more person may say, sir, I want to design a induction motor with 7 phases. Can you please tell? Yes. Day after tomorrow, somebody may ask, sir, I want to design with 11 phases. Can you please tell? Yes. So like this, if one is asking for one phase for one day, then whatever the time that is allotted, I need to spend only on this RMF. So for that, I'll be discussing case 2. What is that case 2 means? What are the conditions I need to satisfy to produce a rotating magnetic field with M phase winding, M phase winding and M phase current. So that we'll see in the next class, right? Now we'll see the question and answers doubts, right? So why? Because I'll be spending some times on the doubts also, as you know that we have to discuss the doubts, right? Just 1 minute, I'll bring that earphones. Right. So we'll see the question and answers now. First, let us see anything in this. So it is not option D, it is option C, Baba. Oh, sorry. Thank you. Right, option C. Why only number of phases? Right. CCW means counterclockwise direction, right? See, there is no like restriction to complete how many days. So it may take some days. So we don't know. So roughly, I think it is 10 days, roughly. So, right, so MMF, Pratyusha, MMF will be stationary. Why? Because, so you can just go through that. So I'll come back. So MMF due to this, see. So if I take a coil, see there is one question. So if I take a coil, see, and if I give the excitation, so this field will be only along this axis. When I'm varying the magnitude of that current, the strength will decrease, but it will be along the same axis, right? So instead of giving a DC, if I'm trying to give an AC, and you know that the magnitude of that current will be changing with the time, then what happened to that MMF? That MMF will be varying its magnitude along its own axis. Pratyusha, I hope you understood, right? Right. See, confused about the speed. Speed is nothing but distance by time. So what is the speed at which that phasor or that vector will be rotating means it is rotating with a speed given by 120 into F by P. So which two parameter decide the speed of that resultant MMF means the frequency of the supply and the number of poles, right? So in case the nature of MMF in DC, so you can see it is a trapezoidal. So your teacher will tell that, right? Please. Right. So remaining things we'll see question and answers. So just I'll give time. Right.
Hello,
Yeah.
sir.
Ha. Yeah, ma,
Sir,
please.
in the starting, we discussed that in the stator slot, we are keeping the conductor in first and sixth slot, then angle is 120. And when we move it to seventh slot, then angle changes. So, sir, can you repeat that part?
See, one thing.
Mm.
See, I told you that. Just I'm going back. Just give me time. Right. I told you that the space angle between the windings has to be 120 degrees electrical. Correct?
Yes, sir.
Ha. So if I'm considering this is one phase with a single turn, right?
Mm.
So you can see on the board single turn. See one conductor I'm placing here and one
Mm.
conductor I'm placing here, right?
Yes,
So
sir.
that axis A will be exactly perpendicular to this. This is your axis A,
Yes, sir.
right? So if I consider the slot angle to be say 20 degrees, the angle between the slots is say 20 degrees. So
Okay.
for 120 degrees by 20, then how many slots I need to place between A phase and B phase? 6 slots,
Six. Yes,
right?
sir.
So
Yes, sir.
if I'm calling this is your phase B, B and B dash, then this B conductor has to be placed 1 plus 6, that is in 7th slot, 7 plus 6 in 13th slot. We have to put the B phase, right? Then
Oh,
this axis will be your B axis. So this will be exactly 120 degrees. So if you are
okay.
properly placing these conductors, that is A conductor in phase A, that is in slot 1, and B conductor in slot 7, then I can say the space angle between those two windings is 120 degrees electrical for sure.
Okay.
Instead
Okay,
of
sir.
that, if I'm placing this conductor B in slot number 6, then definitely the angle between those two faces is not 120 degrees, it is less than that. Will agree with
Okay.
me, right?
Yes, sir.
Then,
Yes.
so the space angle between the two windings is not 120 degrees, it is other than that. Understood, Mano?
Yes, sir. Yes, sir. Thank
Right?
you, sir.
Right,
Yes,
Mano.
sir.
Right,
Thank
Mano.
you.
Right. 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 Yeah. Yeah, please ask.
Observation, sir.
Observations. Yeah, I'm
And పైన ఒకటి మ్యాటర్ టాపిక్ చదివాను సార్ అబ్జర్వేషన్ కన్నా పైన
observations for rotating magnetic field, right? Yeah.
అండ్ పైన ఒక మ్యాటర్ రాపించాను సార్ అది స్పీకా స్పీకర్ సార్ మీరు రాసింది
ఏదమ్మా
స్పీక్ అని రాశారు సార్
స్పీక్ కాదమ్మా ద స్పీడ్
స్పీడ్ రాశారండి
థ్యాంక్ యూ నాన్న స్పీడ్ గివెన్ బై ఇస్ ఇట్ ఓకే మా
ఓకే సార్
రైట్ మా
సార్
రైట్
అబ్జర్వేషన్ లో విత్ ద ఇంక్రీజ్ ఇన్ ద నెంబర్ ఆఫ్ ప్లేసెస్ అదే
ఇది దీంట్లో ఇన్ దిస్ త్రీ
సార్ చెప్పరా సార్ అది
సో దిస్ త్రీ రిప్రజెంట్ హౌ మెనీ ఫేజెస్
3 ప్లేసెస్
three phases. So instead of that three phases, if I place 5 phases, say, then what will be the strength? 5 by 2. That means when compared to three phase, the strength will be still more. Then the torques will be so strong. Understood?
విత్ ద ఇంక్రీజ్ అని అంటే నాకు ఇక్కడ అర్థం కాలేదు సార్ దేన్ని ఇంక్రీజ్ చేస్తే నెంబర్ ఆఫ్ ప్లేసెస్
నేను ఇక్కడ రాశాను అన్న సి with the increase in number of phases means now how many phases we have taken? 3. So if I am taking 5, then what will be the strength? The magnitude increases. Is it clear now?
ఓకే సార్
Right.
సార్ వీడియో చూపిస్తా అన్నారు కదా సార్
అది రేపు నా సి వెన్ ఎవర్ ఇట్ ఈస్ రికార్డ్ ఐల్ షో సో దీనికి అక్కర్లేదు నేను చూపిస్తాను వెన్ ఎవర్ ఇట్ ఈస్ రికార్డ్ ఐల్ షో ఇస్ ఇట్ ఓకే మా
ఓకే సార్
రైట్
సార్ కొంచెం రాయడానికి టైం ఇవ్వండి సార్
ఓకే అమ్మా నేను ఐ షేర్ దిస్ కాపీ డోంట్ వరీ ఓకే సో ఇమీడియట్గా ఇప్పుడు షేర్ చేస్తాను మీకు మేనేజర్ మీకు ప్లేస్ చేస్తాడమ్మా యూ కెన్ జస్ట్ కాపీ దట్ ఓకే రైట్ బట్ స్టిల్ ఐ ట్రై టు గివ్ ద టైమ్ మోర్ సో దట్ యూ కెన్ కాపీ ఏమ్మా రైట్ అమ్మా రైట్ నెక్స్ట్ రెడ్డి
హలో సార్
అమ్మా అడుగమ్మా
సార్ ఇది థియరీలో మనము మ్యాథమెటికల్ ఈక్వేషన్స్ ప్రూవ్ చేస్తామన్నారు సార్
అది కాదమ్మా వాట్ ఐ మీన్ టు సే ఈస్ యువర్ థియరీ మే బి ట్రూ ఆర్ థియరీ మే బి రాంగ్ ఓకే సో ఇఫ్ యువర్ థియరీ ఈస్ హ్యావింగ్ సమ్ మ్యాథమెటికల్ ప్రూఫ్ అండ్ యువర్ మ్యాథమెటికల్ ప్రూఫ్ ఈస్ కరెక్ట్ then your theory may also be correct. So whatever the equations I have derived now, that 3 by 2 times of fm cos theta minus omega t or theta plus omega t, they represent the rotating nature. So mathematically those equations says that equation is a rotating one. So what will be the nature of that mmf means also rotating. So basing on the theoretical proof, as the theoretical proof says that it is a rotating, then I can conclude that with those conditions the mmf will be rotating and field is also rotating. Emma, అర్థమైందా?
ఓకే సార్ సార్ this RMS will be if you take these conditions only RMF is equals to that magnitude is constant like that it is rotating.
Yeah, very good. Ready, correct. So if you are going to fulfill all these conditions, so whatever the field that is produced in the air gap will have a constant magnitude of 3 by 2 times of fm, and that will rotate with a fixed or constant speed of constant speed given by 120 f by p. Emma?
Okay sir. So
right.
can we say that the theory can be molded according to our assumptions, but the law will be same. We cannot change that.
See, it is not a law, it is a theory. That means if you want to produce a rotating magnetic field, then you need to satisfy this condition. Then you can see, or you can have a rotating magnetic field in space.
Okay,
Ardha
sir.
right,
Okay, sir.
right, Amma, right.
Sir, sorry, I
Hmm.
understood all about the explanation about space angle and time angle, but I did not know exact meaning of space angle and time angle, sir.
Space angle, see, when we are talking about the resultant MMF, where it is moving in space, right?
Okay, sir.
Right. So with respect to which axis we are taken, with respect to a axis. So when theta is equal to 0, the resultant MMF is along a axis. Now with the time, the theta is changing. When theta is changing means which angle it is changing internally? Theta is
Internally.
theta is changing means which angle is changing? Space angle is changing. Is it clear? So omega t is equal to 0 means which phase is excited? A phase, right?
So here,
Yeah, please ask Ma. Ready?
hello, sir.
Ready? Clear?
Sir, here both are same, sir. Space angle and time angle.
No, they are not same, right? Space angle means it is the angle along which the windings are being placed. So the time angle is, it is the time with which the peak values in the respective phases are changing,
Okay, okay, sir.
right?
They are different, but in this case, they are same, sir.
Not same. So whenever there is a change in omega t, proportionally there is a change in theta. So when
Okay,
omega t is equal to 0, theta will be 0. That means when omega t is equal to 0, A phase is having a peak value. A phase is along place along which axis? A axis. A axis means theta is equal to how much? 0. So
okay,
when
okay,
that omega t is becoming 120, theta is becoming how much? 120, B phase. So with the omega t, which one is changing? Theta is changing. Emma,
okay, okay, sir. Sir,
right?
can we say that if theta is proportional to omega t only, then the RMS will be produced?
Correct.
Can we say that like that, sir?
Absolutely correct.
Okay,
Okay,
okay.
right, Emma.
Sir, somewhere sir, here you told like n cos theta, no, sir.
Mm.
It pays a n cos theta, and theta is the space angle.
Uh, so it is a mathematical representation of your windings.
So here theta you took and you took a line with the theta, no, sir.
అవును అంటే with respect to a axis, I'm taking one arbitrary axis. When I'm taking on arbitrary axis, what will be that n along that axis?
Arbitrary.
One,
So arbitrary.
one some temporary axis. What will be that axis? N along that axis. If this is a, this is theta. What is the component of a here? A cos theta. So when I'm having n turns along a axis, what will be the turns along that other axis? It is n cos theta.
Okay, sir. So you wrote that a and a arrow between them and n cos theta means a is equal to n cos theta, sir.
A is equal to n. Theta is theta. So here a cos theta. There is n cos theta. N represent the number of turns along that axis A.
Okay, sir.
See,
I did not understand what this line exactly mean. Arbitrary constant means we
see,
will
when you are moving away from axis A, some other axis I'm taking. So how to represent that n along that axis? How many turns are there along axis A?
n turns
So if you are taking one or another axis making some theta from axis A, then how many turns will be there along that axis?
n cos theta.
That's what I have taken.
So this axis also has a winding, sir.
So it is, if I am having n turns on that particular A axis, then on the imaginary axis, the number of turns will be n cos theta.
Okay, okay. There will be no windings, but it is
Yeah,
imaginary that.
correct. So with that
Okay, sir.
MMF will be produced. Emma,
Okay, okay. Yes, sir.
right, ma, right.
Sir, here you told that at somewhere.
Ready, you can just throw the mail by because మిగతా వాళ్ళు కూడా ఉన్నారు కదమ్మా రెడ్డి. Okay, ready. Otherwise,
Sir,
I'll give my number. You call to me, ready. Okay,
okay.
right, Nana, right, right, right. Right. Next. Yeah, Gogineni.
Yes, sir. While reversing the directions, you changed the currents, right?
Currents in any two phases, ma.
Yeah, can we change the phases?
See, what do you mean by phases? See, what are the phases here? A, B, C, right?
Yes, sir.
Instead of changing the currents in, now you tell. So this is your picture. You can tell me now.
The angle difference between A and B is 120. Can we change the positions of B and C?
So you want to see, we are not disturbing this phase sequence. Sorry, these angles we are not changing. See, the
Okay.
question is, I am considering one motor with a 3 windings with a space angle of 120 degrees.
Okay.
And to that motor, if I am giving a 3-phase current with IA, IB, IC, if it is clockwise, and to the same motor, if I give IA, IC, IB, the direction of the field will be reverse.
Yes, sir.
Understood, ma?
Yes, sir.
Right? Okay. Is it clear?
Sir, could you please tell me the phi 2 dash in back EMF part?
That we'll discuss in the working principle, don't worry. But if you want
Okay.
to know, as of now, just I tell you. So whenever you are connecting a load, what
Okay.
circulates through the load? Current.
Correct.
That N2 into I2 will produces one flux phi 2.
Okay.
That phi 2 will be acting in opposite direction to phi m.
Yes, sir.
Then what happened to the flux lines in the core or flux in the core? Decreases.
Hmm.
When decreases, what happened to that E1?
It decreases.
Then what happened to the difference V minus E1 or E1? E1
The
is
difference.
V minus increases. When it
Increase.
increases, so additional current will be drawn from the source.
Yes, sir.
So that N2, that I2 dash into N1 will produce one additional flux, which is in the opposite direction to that phi 2,
Okay.
which is in the same direction as phi m. So phi 2 dash and phi 2 will cancel out, and that flux in the core will remain constant.
Okay, sir.
Is it okay, ma?
Okay, sir. Thank you,
Right,
sir.
right, ma. Thank you. Right, Vikrant. Vikrant.
సార్ గుడ్ ఈవినింగ్ సార్.
Good evening, ma. Vikrant.
సార్ చెప్పిన టాపిక్స్ అన్నీ నాకు క్లియర్ ఉంది సార్, కానీ ఇండివిజువల్ ఫేజ్ నేచర్ ఆఫ్ ది ఇండివిజువల్ ఫేజెస్ ఉన్నాయి కదా సార్,
Ma.
ఎంఎంఎఫ్, వాటిలో ఫేజ్ బి నుంచి రిజల్టెంట్ 3/2 ఎఫ్ఎం ఆ ఈక్వేషన్ వరకు ఒకసారి క్లారిఫై చేయండి సార్.
అదేం లేదు నాన్న. సి దిస్ ఈస్ అ మ్యాథమెటికల్ ప్రూఫ్. ఓకే. సో ఇప్పుడు ఇండివిజువల్ ఎంఎంఎఫ్ దగ్గర ఉంది కదా, ఇండివిజువల్ ఎంఎంఎఫ్ అంటే ఎఫ్ఎం కాస్ రేట్ ఉంది కదా. సో ఇఫ్ యూ ఆర్ ట్రైంగ్ టు యాడ్ అప్ mathematically, you are going to land up with this equation. Which equation? 3/2 times of fm. Otherwise you can go for graphical. What do you mean by graphical? See, if I'm considering these three individual mmfs,
Yes, sir.
so here I want to find out the resultant mmf at any space. So now we are going to find out at some point p. You are standing here in the space and you want to find out the resultant mmf. So the resultant mmf will be the sum of all individual mmfs, correct?
Yes, sir.
So what will be the mmf due to phase A? It is fm. So what is mmf due to phase B and phase C? It is negative direction. It is minus fm by 2 minus fm by 2. That means it is along negative B and negative C axis, correct?
Yes, sir.
So if I'm considering at that point, you can see, so along axis A, we are having a peak value of fm. At the same instant, along negative axis of B, we are having fm by 2. And along negative axis of C, we are having fm by 2. I need to add up all these three. If this is fm by 2, so this angle will be 60. Why? Because this is 120. Then what is the component here? Fm by 2 cos 60. What is the component here? Fm by 2 cos 60. Simple vector analysis.
Yes, sir.
So what is the total? Fm plus fm by 2 cos 60 plus fm by 2 cos 60. The total will be 1.5 times of fm. Along which axis? The resultant, that is A axis. Like that, at every instant of time, So if I'm going to add up all individual MMF, then you can see in the space, the peak value will be 1.5 times of FM and it will be moving in space. Is it clear, ma,
Okay.
Vikram?
Yes, sir.
Right, Anna, right. Thank you, Vikram.
Thank you, sir.
Right, ma. Right, next.
Hello, sir.
Yeah, ma, please. Pratyush.
Sir, you said that for taking mathematical equation to represent the number of turns in a space, we have taken n cos theta, no, sir.
No, no, ma. See, the thing is, see how many turns are there along A phase?
N turns, sir.
N turns. Otherwise, see, if anyone asks, see, this is phase A with how many
Yes, sir.
turns? N turns.
Yes, sir.
This is phase B with how many turns? N turns.
And
This is phase C with how many turns? N turns. Correct?
yes, sir.
Right. So what is the current you are passing here? Im cos omega t. So what is the current you are passing here? Im
M
cos
cos
omega t minus 120. Im cos omega t minus 240. Correct?
yes, sir.
Now I want to find out the resultant of all these individual MMF along this axis, some axis, imaginary axis I need to find out. So
Yes,
which I
sir.
am making it as theta here.
Yes, sir.
Now if anyone asks her what is the resultant of all this MMF along this axis, means I have to find out MMF due to this phase, MMF due to this phase, MMF due to this phase. Correct? All three phases.
Yes, sir.
Right? So what will be the MMF due to this phase? So it is N Im cos omega t. So what is the component here? Cos theta, means it is cos theta. Correct?
Yes, sir. Yes, sir.
Then here to here it is 120. So here it is 120 minus theta. Correct?
Yes, sir.
So it is Nim. So what is the current that is flowing here? Cos omega t minus 120 into cos. What is the component here? It is cos 120 minus theta, or I can write theta minus 120. Why? Because cos theta or
Cos
cos
of
minus
yes, sir.
same. Plus what is this component here? So it is Nim cos omega t minus 240 into cos theta minus 240. So this is the resultant MMF along this axis due to all. So this is what I have written there. Is this point clear?
Yes, sir. Yes.
Pratyush, is it clear, ma?
Yes. Yes, sir. Sir, I am asking that means if we go on moving away from if we go on moving away from phase A, according to this equation, number of turns are decreasing, no, sir. And cos theta is increasing and cos theta is decreasing, no, sir.
So this is decreasing. What about this B phase? Now it is aiding. When you
Yes,
are
sir.
moving away from A, you are closing to B, then that is increasing. That is the reason 3/2 time FM remaining constant.
Okay, means in practical scenario in motor there will be no that not like that, no, sir. Means every phase have same turns, no, sir.
It is same terms. I mean to say that if you want to find out the resultant along some axis,
Yes,
which
sir.
is making an angle theta, then you need to find out the MMF due to this phase, this phase, this phase. And if you are finding out that it is 3/2 times of FM cos theta minus omega t. So which
Okay,
is
sir.
a rotating one, I mean to say. Understood?
Okay,
This
okay,
is
sir.
what
Yes,
I
sir.
tried to explain. Understood?
Okay, sir. Yes, sir. Yes, sir.
Right, right,
Thank you, sir.
right. Right. Next, Hemalata.
Yes, sir.
Hama, please ask.
Sir, is it audible, sir?
Yeah, ma, you are audible to me.
Sir, you said in reversing, sir, in reversing RMF, we have got the equation now, sir, according to the resultant MMF.
Ma, it is theta plus omega t.
Sir, will you say the relation between phase shift and the time, sir?
You see, I didn't get your question, Mahemalata. Can you please?
Sir, in case of normal, in case of not reversing MMF, we got theta proportional to time, sir.
Here also theta is proportional to time, but with respect to time, the theta will be in opposite direction. So with omega t, it is moving in opposite direction.
Okay, sir.
It is not in the same direction. It is in opposite negative theta direction. It is moving.
Okay, sir.
Understood, ma?
Yes,
Why?
sir.
Because when omega t is equal to 1, then theta should be equal to -1. So what is the importance of -1? Theta is not minus. So minus indicates it is in the negative direction.
Okay, sir, that means phase shift is in opposite direction.
Yes, ma. Correct. Shifting,
Okay.
not phase shift. Shifting is in opposite direction.
Okay, sir.
Right, ma? Right.
Thank you, sir.
Right, ma. Right. Right. Sagar.
Good evening, sir.
Good evening, Sagar.
Sir, I have a doubt in yesterday's class, sir.
Yeah, you can ask Sagar.
Sir, you said compared to straight coil, a circular coil has a more magnetizing strength now, sir.
That your EMF teacher will explain, don't worry. So he'll derive that the intensity due to a long conductor carrying current and the intensity due to a straight current carrying conductor and a circular current. Your teacher will discuss, don't worry. If it is
Sir,
required, I'll
one
discuss
more.
at the end. I'll discuss at the end, don't worry.
Okay, sir. Sir, one more doubt. Sir, sir as you said, when we attach a permanent magnet to any prime mover, we get a non-uniform magnetizing force, no, sir.
I never said like that. See, if you want to get a rotating magnetic field, take a permanent magnet, connect it to that external prime mover. If you are moving that, the strength is uncontrolled. That means as a permanent magnet, we don't have the provision to increase the strength or decrease the strength. That is uncontrolled field, I told. Okay.
But it has constant flux, no, sir. Then how it is becoming uncontrolled?
It is constant flux, correct. So if I want to increase the flux,
We cannot, sir.
if I want to decrease the flux,
We cannot.
if I take a electromagnet, can I increase the flux?
Yes, sir.
Can I decrease the flux?
Yes, sir.
Right. That is the meaning of telling controlled and uncontrolled. Is it okay now?
Okay, sir. Thank you, sir.
Right. Ramakrishna. Right, Ramakrishna.
Yeah, hello, good evening, sir.
Good evening, ma.
So in synchronous motion, you have taken that 120 by 20. So what is that 20, sir?
See, 20 is the slot angle. Let us consider not synchronous machine.
You have assumed it. Okay, sir.
Yeah, I assumed that. Ramakrishna.
Okay, that was a doubt. That's it.
Right, ma. Right.
Thank you.
Right. Right. So I'll stop for today. So no one is raising the doubts. We'll stop.